This is our second batch of the introduction to performance-based design and introduction to resilient-based design. I feel that these two topics are very necessary because uh, this topic has been used by other countries for more than 2 decades already. And I feel that this topic has to be shared to everybody so that we can advance our professional service as a structural engineer. Anyway, so I divide this into two topics. So we have introduction to performance-based design again, and the introduction to resilient-based design. I'll now share you the slides. By the way, this is the second batch, but our batch one was attended by about 500 participants, and it was attended from all over the world. We have participants from USA, from Brunei, from Bangladesh, another from Singapore, no, and other countries. And I'd like to thank you all for joining our technical seminar about the two topics that I have mentioned. Okay, so basically, the topic number one will discuss about the introduction to the performance-based design, and topic number two, which will take about 2 hours, about the introduction to resilient-based design. Okay, now question is, what will you do if earthquake will happen in 1 second, in 2 seconds, or in 3 seconds? Well, maybe a lot of us will just duck, hold, and cover, or some of us may run, some of us may look for an open space, or anything that can protect us from any falling hazard, no, inside our structure. And this could be the ceiling, this could be the wall, this could be the furniture, no, and other utilities of the building that becomes hazard to the occupant, or it may be the structure itself. So that is why in performance-based design, I will discuss basically here the next generation of PBD. It's not just about the immediate occupancy, collapse prevention, or the life safety performance level, but what do we really intend to design building using this approach? Okay, so in this is the slide where I took this from the UC Berkeley when I attended the conference in January in the US. So they estimated a lot of people died during calamities like earthquake, but normally when there's an earthquake, uh, there's also a tsunami and typhoon, no, or hurricane. So it kills thousands of people, and normally these casualties is even more than the casualties that is happening now because of the coronavirus. So that's why Metro Manila uh, Development Authority in coordination with JICA, with DOST, PVOX, and other government agencies in the Philippines, they conducted in 2004 what we call Metro Manila Earthquake Impact Reduction Study. And based on that study, they estimated to have 34,000 casualties and 240,000 injuries due to scenario earthquake of magnitude 7.2. And this is due to the valley fault system that traverse Metro Manila. So we can see this casualties 34,000 is really too much that I don't know how we can address this as structural engineer or as part of the community that we can mitigate at least the impact of these casualties. And these casualties is attributed to the collapse of the building or damage of the non-structural component of the building. So that's why it's not just about the earthquake that we have to talk about, but it's also the building that is subjected to the earthquake. How vulnerable is our structure when subjected to earthquake? Well, historically, we have this progression of structural engineering. We know that for a long time, we don't have the building code. So we just design buildings, structures, bridges based on our intuition. So that's why we call that the intuitive design. But with the innovation, no, of science and technology, we were able to, and this is an example of an intuitive design. No? So some of this structure were built for 100 years in the Philippines. And this is just made up of either a coral stone when the structure is near the sea, or um, sometimes this is made up of bricks, or sometimes this is made up of adobe stone. So whatever is the material available uh, near the specific site. Okay. Now after that we have the code base. So most of the time our buildings, or maybe 95% or even more of our buildings, were designed based on the code base approach. And of course, there are some buildings in which the code base approach cannot be used because of the limitations. For example, if the building have a weak story or a soft story, or sometimes we have a wall system above but we have the columns below, of course this is no longer compliant to the code based on the specified structural systems. So with that, code-based approach no longer applies. So after that, we also have the consequences and risk-based design. So this is a design approach where we really have to consider what are the risks around our site or the site of the structure. And then the last is the resilient-based design. So in resilient-based design, just to give you an overview, uh, this is 4 steps higher than the typical code-compliant building. So this is a design approach in which we can actually minimize or even make our building zero damage, including the content, if we really have to design our building using the RBD approach. Okay, now the first code that recorded, no, in the history of man, maybe was the code of Hammurabi, that states that if a builder of a house, or if a builder build a house for someone and that doesn't construct it properly, and the house that he built fall in and kill its owner, then the builder shall be put to death. But because of the experiences that we cannot really prevent the earthquake from shaking and a lot of buildings really be damaged, so this building code was changed. No? So we have this building code, or we call the code-based structural engineering, in which we have the set of rules that specifies the standard for constructed objects, such as buildings and non-buildings. But definitely, this code-compliant building limit the damage or limit the buildings to from collapse. Okay, so we have a lot of building codes all over the world. Of course, we have the British code, we have the Euro code, we have New Zealand, we have Japan code. But if you have to think of it, these codes are not the same. So the question here is, if these codes are not the same, which among these codes are correct? Okay, so, but remember that we structural engineers follow the same one equation, which I will discuss later on. But the codes and the standards that they set for different building codes depends on their experience, based on their capability to develop technologies or science. Okay? Now in chapter 11 of ASCE 7-16, this is the minimum design loads and associated criteria for buildings and other structures. It is very clear that the specified earthquake load that we use in the design of building are based upon the post-elastic energy dissipation of the structure. So when we say post-elastic, we allow the material or the component, no, structural component of our building to yield beyond the elastic limit, meaning beyond the stress in which the material will go back to its original length or undeformed section. Okay. So in the National Building Code of the Philippines, it is also very clear in Section 102 that, I will read this for you, it is hereby declared to be the policy of the state to safeguard life, health, property, and public welfare consistent with the principle of sound engineering management and control, and to this end, make it the purpose of this code to provide for all buildings and structure a framework of minimum standards and so on. Okay? But if we're going to look at the referral code, our referral code in the Philippines, uh, in section 208 of the NSCP is very clear that the last sentence, these provisions are not intended to assure zero damage to structure nor maintain their functionality after a severe earthquake. So meaning if our building, a code compliant building, similar to the US code, when this building is subjected to earthquake, we really expect damages or even collapse. Okay, even collapse because later on during the PBD, I'll tell you what's the probability of collapse of these structures that are even designed using the PBD. And remember that the PBD approach is a step higher than the code base. Okay, now this is the plot of the displacement versus the base shear of our structure. So as you can see, this part here, this part, we can see that the maximum stress is VA. Okay, so this part here, sorry. Uh, this part, the vertical axis is the VA, no, or that's the design earthquake, elastic design earthquake, or rather the elastic earthquake, and we have the corresponding elastic displacement, delta E. Okay, but remember that in the code, we design our building not based on that V elastic, but rather we design that based on the V or the static base shear. So meaning the elastic earthquake is actually divided by the response modification coefficient, that is R. And R ranges from 2.2 up to a value of 8.5 depending on the ductility of the entire system. Okay, so meaning we really allow the structure to deform beyond the elastic limit, and with that, we expect yielding of the rebar and crushing of the concrete. Okay, so that's why in the code, this is the picture that I took from ACI. So this is the cross section of a column. You can see that this column is provided by a lot of hoops. Okay, and the intent of this hoop is two things. Number one, aside from resisting the shear, of course, no, but there are most important thing why we need this hoop in column and in beam, because number one, this hoop will contain the concrete inside the core in case the concrete will crush during the strong earthquake. And number two, this hoop being spaced at 6 inches as the maximum, or 6 times the diameter of the main bar, is to prevent buckling of the main bar the time that the concrete cover of this column will fall off. So you see, just to make sure that the building, quote unquote, can be prevented from collapse, what the code is saying is just to provide a lot of hoops to ensure that the concrete inside the core can still provide support for the gravity load, and with that, the people have enough time the occupants will have enough time to evacuate outside the building. So that's the code as of the moment. Okay, and I took this picture from PEER, Pacific Earthquake Engineering Research, and ATC, the Applied Technology Council. Look, if you can see this shear wall, this shear wall was designed so that the plastic hinge will occur just above the ground floor. Now, to make sure that this shear wall can still support the gravity load after the very strong earthquake, the code allows us to provide boundary element. And this boundary element is provided again with a lot of hoops to make sure that the concrete inside that boundary element can still support gravity load and people have enough time to escape or evacuate outside the building before this structure will finally collapse. You see that? That's what the code is doing. And even coupling beam, it is designed to have a diagonal main bars because these diagonal main bars will have a vertical component and a horizontal component. And this vertical component of the diagonal main bar is the one that will support the shear the time that the concrete in a coupling beam will burst. So that is why if you look at the equation to calculate the shear capacity of a coupling beam, you can never see the capacity of concrete because it is expected that once the coupling beam is subjected to a strong shear, ties cannot resist the shear. The coupling beam, the concrete in the coupling beam will just burst because we have a much rigid shear wall. And with that, the codes say that, okay, just use the just use the uh, vertical component of the diagonal bar to resist the shear. Okay, so this is the example of buildings that collapse during an earthquake. Well, that were damaged during during a very strong earthquake. Okay, so and you can see that this damage of the concrete occurs at the joint. And then the code developer say that, okay, if we're going to allow damage of concrete structure in the joint, it's quite more dangerous because if the column and the beam will develop plastic hinge at the joint, then the column can no longer support vertical load. Okay, so that's why right now we have this requirement from the building code that the column must be 20% stronger than the beam. We call that the strong column weak beam requirement. And number two, we allow damage in the beam not at the joint but at distance 2h from the face of the beam. So we call that the point of plastic hinge, or we call that the confined region. Okay, so this is the same damage of a building during the New Zealand 2011 earthquake. So still a lot of damage, even we comply the new code. Now, basically, the intent of the code is to protect lives in the largest earthquakes likely to affect a building. And number two, to reduce property damage and economic loss in more frequent or moderate earthquakes. Okay, so that's why the performance of the code to earthquake is basically from around magnitude, approximately magnitude 4 or less. We have the so-called performance level of serviceability limit state, meaning in this magnitude, at least the building component should have no damage at all because everything is elastic. Okay, and this magnitude 4 normally occurs every 10 years. So meaning the recurrence interval is around 10 years. Now the second is the control limit state. Approximately this is the performance of the building with a magnitude between 4 to 6, and the recurrence interval of this earthquake is around 20 years. So the control limit states, this is where we allow some yielding of the rebar, some damage in the concrete, but the building is quote unquote. They say that some of these are still repairable. Okay. Uh, and the last performance level is what we call the survival limit states. This is where the earthquake becomes higher than magnitude 7. And after this earthquake will occur, this is what the code is saying, that the building can be irreparable and impractical to, to retrofit. Okay. Now, another question here is, well, this is the code performance level, but what will happen beyond that? Are we going to demolish the building after or retrofit? Okay, so this is the unknown after a very strong earthquake of magnitude 7. Okay, but as I've said, I repeat, some of them that okay, building is repairable, and that's what the code is saying. Okay, okay. Now, basically, if this is the building that is subjected to gravity load and also subjected to horizontal ground motion due to the effect of an earthquake, the equation of motion is very simple. So if we have a single degree of freedom, this is just equal to the mass times the acceleration plus the damping times the velocity plus the stiffness times the displacement. And then this is equal to the negative of the mass times the ground acceleration. So this equation of motion is very simple, but of course, the code simplify this into uh, another equation, which is called the base shear. And CS here is the seismic coefficient that is dependent to the ductility of the structure, the period of the structure, and some say that, okay, that's the significance of the structure. So that's why we have uh, uh, importance factor I that involves in this CS. And after that, we can distribute this base shear, meaning the equivalent horizontal force acting at the base. We can distribute this horizontally to every floor, and we can use static, or any theory of structure method to apply this. But in the code, it's simply the summation of the weight times the height of the floor above the ground, and then divide this by the summation of the total weight times height of each floor. Okay? And then we can now distribute this as F1, F2, and F3, and then calculate the shear in the moment. Okay? But the main problem actually here is there are only two things. Number one is, what's the stiffness that we use? In the code, we just simply use 0.7 for column and then 0.35 for the beams. Okay? Now, the backdrop of the code is, if you're going to use a very stiff column, meaning a very strong column, a very rigid column, uh, the figure on the left, you can see that whatever is the ground acceleration, the acceleration of the mass will also be the same as the ground acceleration. So can you imagine that if the ground acceleration is, let's say, 2 of g, and you have also a floor acceleration of twice of the gravitational acceleration? Definitely, every content of the building will be damaged. Some of them, like the walls, ceiling, utilities, might collapse because of that. Okay? But the positive side of it is that there's no displacement in the column. So with that, if the column will not displace, definitely this column will not be damaged. And the wall that is parallel to the plane of the frame might not also be damaged. Okay, except the outer plane. Okay. Now, if we have the flexible structure as the opposite, you can see that whatever is the ground acceleration, that cannot be transmitted to the mass if we have practically zero stiffness of the column. Okay? But the downside here is if we have a very flexible column, then whatever is the ground displacement will be the same as the displacement of the mass. And with that, we expect a lot of drift in the column that will cause damage to the column and again to the walls or other non-structural component. Okay, so that's the downside, no, of having a flexible structure. So if you're going to look at the comparison of rigid and flexible structure, you can see that the rigid structure, we have a relative acceleration that is very high or equal to the acceleration of the ground. And then if we use a flexible structure, this becomes zero. And the opposite of that is the relative displacement of a rigid structure is zero, but it becomes equal to the ground displacement if we have a very flexible column. Okay? So that's why the code say that, okay, why not limit the story drift to about 1% to 2% or sometimes 2.5% depending on the period of the structure. So this is our practice using a code-based approach. Okay? And then this drift is very important because the figure on the left, you can see that the drift can be distributed, or meaning the deformation of the column can be distributed over the floor if we have a uniform stiffness. But if we're going to have a stiff wall, this wall can be structural or maybe non-structural, which most of the time the CHB masonry, for example, is just attached directly to the column. Then that frame becomes rigid, and therefore this will develop a weak story behavior. And that drift is now concentrated in the lower column. So this is most of the time the failure of typical structures with this type of construction. Not about design, because of course we don't design like this. Number two, this is not allowed in the code. This is allowed up to 9 meters or not more than 2-story, but beyond that, it's no longer allowed by the code. Okay. Now, so the basic dilemma is how to minimize the inter-story drift and floor acceleration simultaneously. So that's what we need to solve, because mitigating the story drift, meaning using a stiff column, it will lead to amplification of the ground motion that will cause a higher floor acceleration that can damage the content of the building and other non-structural components. It is also dangerous to sensitive equipment like a generator set, unless it is being isolated from the floor. Okay. Now, if we're going to mitigate the floor acceleration, meaning the solution is we're going to use a flexible column or flexible structure. But this flexible structure will lead to a larger interstory drift that, as I've said, it will allow a lot of damage in the column or shear wall or braces and also non-structural component. Okay? So that's the two basic dilemma. So uh, another backdrop of the code is that the structure is designed in the range of frequency that is higher than the earthquake energy. Meaning the ground motion is very strong, but we design our building to a lower frequency by using a flexible structure. So we use this equation to do that, to get the equivalent base shear. Number two, the earthquake energy is dissipated by the structure itself through the inelastic behavior of the material. So that is why, as I've said, instead of using the elastic earthquake, we divide it by R. And if we have, for example, irregular structures, we have connections, we design that connection to have the maximum earthquake stress, the force that can be generated by the structure. So we multiply that by the overstrength factor, which is normally around 2.5. Okay. And next is we use the strong column, weak beam theory. So just to make sure that the building, just to make sure code, that the building will not collapse, we use this strong column, weak beam theory, in which the column must be 20% stronger than the beam moment, and with that, bending moment fails in the beam instead in the column. Okay, so that is how the earthquake energy is being dissipated. But of course, it's a waste of our structure. We allow the structure to be damaged. We use the structure as the fuse to absorb that earthquake energy. Okay, and then the last is the ground acceleration generates higher inertia forces that could damage the content of the structure. Okay, now the limitations of the building code, I took this from FEMA P-58. FEMA realizes that, number one, even modern buildings designed to current code have some chance of collapse in earthquake or might need to be demolished. I will repeat. This statement came from FEMA P-58. FEMA, Federal Emergency Management Agency in the US. Number two, the building code does not address many aspects of a building that affect financial loss and whether a building is functional after an earthquake. Number three, code compliant buildings are designed to resist forces from an earthquake of a particular intensity, even though larger earthquakes are possible. So take note that we are using the 10% probability in 50 years. So that is the design earthquake that we use. That is what we derive, and we can create our own response spectrum curve, RSA, and convert that into PSA, or the pseudo spectral acceleration. That earthquake was taken from several earthquakes, but usually those are from earthquakes with 10% chance in 50 years, meaning that the recurrence interval is 475 years. But earthquakes can be stronger than that. Okay? And then the last is most communities do not require all their buildings to be evaluated or retrofitted, even for known earthquake vulnerabilities. Okay? Okay, so that's why we have the PBD. So with this PBD, okay, uh, we can at least predict some damage and extent of damage of our structure, both structural and non-structural. Okay, now the PBD, or the performance-based design, based on the definition of ICC, International Code Council, it defines as an engineering approach to design elements of a building based on agreed upon performance goals and objectives. Engineering analysis and quantitative assessment of alternatives against the design goals and objectives using accepted engineering tools, methodologies, and performance criteria. Okay, but of course there are other performance based design definitions. Okay, now this started actually from the CIOC, and or the Structural Engineers Association of California Vision 2000 report in 1996. Okay, so that they say, okay, what if we design our building to be fully operational, meaning the building must continue its service with negligible damage to structural and non-structural component. Okay, or I'll go to the last first. Or the collapse prevention, where the damage is severe, but structural collapse is prevented. Non-structural elements may fall, but repair is generally not possible. So these are the two extremes performance level that was set in 1996 by SIOC. And the next is the operational performance level. Okay. Now, most operations and functions can resume immediately. Structure is safe for occupancy. Essential operations is being protected. Non-essential operations disrupted Repair is required to restore some non-essential services, and damage is light. Okay. And then the next is the life safety. So we have a moderate damage, structure remains stable, selected building system, features or contents may be protected from damage, life safety is generally protected, building may be evacuated following an earthquake, repair is possible but economically impractical. Okay, so these are the performance goals. Because historically, in 1911 up to 1997 and up to now, 2020, okay, don't you know that the base shear that we use in design ranges from around zero point 0.1 to around zero point 0.2 depending on the seismic source, how far is the building from the earth, from the fault line, causative fault line, what's the type of the soil, type of occupancy. You know, these are things that we consider, but generally it's around zero point 0.1 to uh, zero point 0.2, and in typical buildings like 5-story or even less, we can even get as much as 0.15. Okay. So, and then when we get that static base shear, we'll multiply that by the total dead load, so we can already get the base shear, and from that base shear, we can distribute that each floor, and then we can now use any method to distribute these forces to all the structural components like beams and columns. Okay. So in the previous approach, historical approach, we just use linear elastic, we use the working stress design, and after that, we don't know what will happen to the building, so we have a lack of knowledge on earthquake demand and building capacity. Okay, and then we just, as I've said, divide it by any value of factor of safety, whether 2, 2.5, or whatever value. And then after that, we were able to plot the response spectrum curve. Any ground motions can be plotted with respect to the spectral acceleration with respect to time, or we can convert this into displacement with respect to the force. But again, this elastic force from earthquake is reduced by the numerical coefficient R, and after that we use that value to design our structural component. Okay. Now in current code, so we're able to develop the performance point, and this performance point is the spectral acceleration intersection between the spectral acceleration and the low displacement curve of our structure. Okay, so the UBC, the Uniform Building Code, was published in Arizona in 1927. Okay, so almost 100 years old already. But as I've said, until now, we still use the same amount of base shear. It's just around zero point 0.1 to zero point 0.2 of the total weight of the structure. Okay. And after that, we have the UBC, IBC. We already have the latest IBC. So this 2015. So questions before by the building owner is the insurance company or some or the bank. What will happen to my structure if I follow the code? And then they say, well, maybe some structures will have damage. And then they say, well, what will happen if I will want a building that remain operational after an earthquake? Code says, okay, maybe we can multiply that by 1.5, that's enough. Okay. And then if you multiply that by 1.5, question is, what will be the extent of the damage? And then some say, okay, what if I follow or I want my building to have severe damage but will not collapse after a very strong earthquake? And then some say that, okay, maybe we can multiply that by 0.75. The building will not collapse. But another question here is, okay, what would be the probability of collapse if we're going to multiply the code by 0.75? So these are questions that were not answered by the code. Okay. And then some of the insurance company say that, okay, what if I will get you an insurance, or from the bank, I will lend you money as long as the damage of the building when subjected to a very strong earthquake is at least 20%. So that is what they call PML, or the probable maximum loss of 20%. Okay? So with that, therefore, engineers made a lot of pencil pushing, okay, to solve this problem. Okay? And then we realized that uh, this can be done. The damage can be done. The damage can be estimated based on rotations of structural components, based on strains, based on deformations. So that's why they documented a lot of performance criteria from the first volume of PBD, which is the ATC, or Applied Technology Council Volume 1. And then it was adopted by the NERP. And then it was finally adopted by ASCE. So this ASCE is the latest version. So there's another version of ASCE coming up in 2022, so 2 years from now. So this is now the evaluation of existing structure, but this document can also be used for the new structures. Okay. Now, performance objective. The performance objective is the desired performance level to a given earthquake ground motion. Okay, so that's why this is the certain probability of occurrence of an earthquake, whether that is uh, an earthquake with a magnitude 4 with a recurrence interval of 10 years, or an earthquake with around magnitude 4 to 6 with a recurrence interval of approximately 20 years. Okay, so that's the earthquake record that we have, or earthquake ground motion that we have to use in the analysis, given a performance criteria of our building. And this performance can be structural or it can be non-structural. But in the next generation of PBD, another question is, well, what will happen to the content? What will happen to the furnitures? What will happen the to other contents of the building, like if you have a data center? Okay, so it's not yet included so far in the PBD approach. Okay, so the PBD pertains to the condition of the building after a certain probability of occurrence of extreme event like an earthquake, okay, or such an earthquake. So there are four contexts of PBD. Okay, the first one is uh, we can design for a higher performance. This is for new construction, meaning the design for performance that is better than the code conforming building. The owners will work with the design team to define the levels of acceptable losses, and then improve design flexibility. PBD can be used to show that deviating from the code or uses an innovative system or material will perform equivalent to or better than the code compliant building. Innovative because we have a lot of materials that are available already in the market but still not in the code. For example, the one that Japan is developing now, they develop already a stranded wire using carbon fiber. They develop already a deformed steel bar, uh, quote unquote, deformed bar using carbon fiber. It is very lightweight, 10 times stronger. It is deformed bar so that it will develop enough bonding. They tested a full-scale bridge with its reinforcements, and it works. But it's not yet in the code. So meaning using the PBD, we can use those data, the low deformation behavior or the material behavior of that carbon fiber, so that we can apply that in our design. Okay. Now, for existing building, so we can evaluate the risk of the building properly. For example, if there's an investor or owner that wants to buy a building, at least the owner know the will know the performance, the seismic performance of the structure before they can invest into that property. And then effective seismic retrofit. Okay, so seismic retrofit can be selected based on the desired performance level and will provide owners a detailed information about the earthquake risk. Okay, so this is the flow charts of PBD process. So we have discussed performance goal based on what is at stake, consider the risk of the occupant, the contents, okay, the activities in the building, assess realistic and worst case scenarios for shaking and damage, determine recovery needs after an earthquake, okay, and then we can bring people on board to assemble a qualified design team, educate and involve key stakeholders in setting the performance goal, develop business case for a desired level of performance, and then create an initial design. Okay, so use a conceptual design tool to make a ballpark estimate, and then comply with the legal requirement of the building code to demonstrate equivalent performance. And of course, check the results and adjust. So we can refine our design, and then if we're able to achieve the performance level relative to our structure, then we can stop and then finalize the details and then implement the construction. Okay, so this is the next generation performance level. So this is just illustrative, okay, for you to see that if we have a new building, for example, we can install protective system. So the casualty risk is practically zero, and then the chance of post-earthquake placard, meaning the chance that our building will be posted by red, meaning nobody can enter that after an earthquake. Okay, and then the downtime of the business operation could be few days. Initial cost is higher, but the repair cost is smaller like that. Okay, but if we're going to follow basic code, for example, for a moderate earthquake, we expect minor damage like, well, what happened in Davao in the southern Philippines. A lot of buildings was damaged due to a magnitude 6.5, very minor earthquake or moderate earthquake, but it affects a lot of existing buildings. Okay, and then for major earthquake, we can have major damage and then 2% probability in 50 years, meaning rare event, buildings will not collapse. Okay, so but of course the casualty risk is a bit higher. The chance that we have a post-earthquake placard is higher. The repair could be months or maybe repairable. Okay, and then if we do not retrofit the building for older buildings, for example, so we have a very minor earthquake, a moderate earthquake, 20% in 50 years, but the damage is severe. And then there's a big chance that the building will collapse after a very strong earthquake. Okay, so this is an example on how to present the cost analysis. Okay, for moderate earthquake, for example, on the left, you can see on the left graph, we have damage, moderate damage, okay, or maybe minor damage due to that earthquake. And then for design level earthquake, usually this is the code-based approach, 10% probability in 50 years. So we have that higher damage. And of course, for the MCE or the maximum considered earthquake, we have extreme damage and buildings can be repairable. Okay, so we can estimate the damage in the connection, ceiling, partitions, exterior, mechanical, maybe content of the building, okay, and other things to be considered as part of the content of the structure. Okay, so I took this statement from one of the book from Jeffrey Solage, the senior structural engineer of in Portland, Oregon. He said that we started taking the seismic performance of our building seriously when we realized that a large earthquake impacting in one of our manufacturing facilities could cause us to miss a product cycle, and that is unacceptable. Okay, so in as guidance for you to as a guide for you to set a performance goal. So these are four uh, criteria that you can consider. Number one is activities in the building. Okay, so you may ask, what is the building used for? Because right now, even if in the code, even if you have a high-rise building, importance factor is still one, but actually it houses thousands of people. If we have a mall that houses like 10,000 people, importance factor is still one. If we have a hospital that houses only, let's say 200 people, we can use this as an essential facility, and then we can use importance factor of 1.5. But actually, uh, once a mall, for example, will collapse and cause injuries to the occupants of 10,000, it cannot be accommodated by one of the biggest hospital that we have. Okay, so those are some considerations that we have to include in our design. Okay, another one is for activities in the building. So which activities are mission critical or will affect relationship with competitor or partners or the reputation of the organization, or can the activities be conducted anywhere or in any place, meaning can we transfer that activities and how much it will cost to transfer those activities, for example a school building or a hospital. Okay, um, how could the activities in the building be affected by the loss of utility or lifelines in the buildings, like electricity, gas, water, internet? Okay, how difficult or costly would it be to relocate the activities if the building is unusable for an extended period? Okay. Now next is occupants. How many people use the building and how much time do you spend there? All day, 12 days, 8 hours? Are any users of the building particularly vulnerable, such as children and elderly? How challenging or time consuming would it be to replace or repair the content of the building? Okay. Other archives, painting that are very expensive, and there are many other things that we have to consider. And then the post earthquake recovery, what is at stake for the organization if this building is unusable for weeks to months or years during repair? Okay. Uh, is the building required for emergency response or other activities immediately after an earthquake? Okay. Could reputation, public relation, or brand be affected by what happens to the building? For example, there's a condominium owned by somebody. How could that affect the reputation that condominiums will collapse? Okay, and of course, the important cost and logistical consideration here because of the time for setting the goal, discuss with the client, analysis time, structural elements, and of course, other things to be considered in the performance of this method, the PBD. Okay, now, what is PBD to engineers? Well, the key to PBD is about nonlinearity. This is just about the nonlinearity of the material, of the cross-section, of the member, or even the geometric nonlinearity. We know that material, after it will develop the elastic behavior, it will deform permanently and it will not go back to its original length. So therefore, the damage, for example, of a concrete beam can be estimated by strain in the column or a strain in the concrete, strain in the rebar, or the rotation of the member itself. Okay, so but remember that what the one that is written in the ASCE that was used for a long time, more than 2 decades, and even in the commentary, those rotations were admittedly by the code as too much. Okay, but so far it hasn't been changed for a long time. Okay, now as I've said, the non-linearity can be from the material. For example, if we have a confined concrete, that concrete can be stronger than unconfined concrete. That is why in the By the way, you can if you want to learn more about the strength of confined concrete, you can study the research of Mander, and this Mander model is already adopted by ETABS. So if you are using an ETAB software, you can well, and even in other software anyway, it's adopted already. Okay. Now that confinement can make the column more stronger as compared to the unconfined concrete. Okay? Remember that what we are doing in practice is we test the concrete strength from the cylinder either 6 inches diameter by 12 inches high or 4 inches by 8 inches high cylinder. But in the real world, we have a concrete with a different cross section and of course confined by a steel bar. So therefore, there's really a big difference between unconfined and confined concrete strength. That is why if the design is compliant to the code in PBD, we have to multiply the strength that we get from the cylinder, multiply that by 1.3. We call that expected strength of the concrete. Okay. So after that, we also have the non-linearity of the cross section. So if the beam, for example, is subjected to a moment that is less than the cracking moment of the concrete, then that beam will behave like an elastic beam. But the time that partly the concrete will crack, meaning develop a tensile strength beyond the rupture stress, this is now the time where the steel bar develop tensile stresses, and from there we have elastic plastic behavior. And if you continue to bend that beam, it will develop the plastic behavior, meaning the steel bar will continue to elongate, continue to deform, but the moment capacity will not increase, and therefore the rotation will further increase. Okay? Now the next is the member. So for member nonlinearity, we have elastic. Again, if the beam is subjected to a stress less than the cracking, so and then it will develop elastic plastic behavior, and then it will develop a plastic. So meaning if the damage is only occurs at the point of maximum moment, another part of the beam is subjected to zero moment or less than the cracking moment, meaning we can never assume that EI or the stiffness of our structure is constant. So that's actually the shortcoming of the code. Because when we design column, for example, we use linear elastic, we assume that the stiffness of the entire column is 0.7 of EI, even if the moment is zero. So remember, if the moment is zero in any structural component, the stiffness of that element is EI, meaning the gross stiffness. But the time that is bended and the concrete will start to crack, the stiffness will reduce to EI crack. Okay? And finally is the geometric nonlinearity. So this is where we conduct second order analysis, especially if our column is flexible or meaning slender. But remember that whether the column is slender or not, you may you may have to consider this one. But the code say that okay, if the second order analysis, second order moment is less than 10%, you can just use the primary moment and stop the iteration. Okay, so this is the beam, for example, and as you can see, this beam is subjected to a uniform loading. So at the support, we have a 45-degree crack. This is because we have that uh, shear, maximum shear, and the moment is zero. We call that the D region, meaning disturbed region. Uh, so the damage is practically due to the shear. And then we have this in the middle, we call that the B region. So B region is practically the part of the beam in which the damage is purely caused by bending, not due to shear. Okay. So how PBD adapt this very simple graph. I'll show you this first. Okay, I'll stop sharing this slide first. Okay. Okay, I want to share to you my iPad so that we can discuss partly how the code develops and adapts this concept no in PBD. Okay. Okay. So this is the beam. Okay, and we have supports, and then of course the load. And take note that if we're going to cut this beam here in the theory that we use in the design of the beam, we say that okay, the section that is plane before bending remains plane after bending. Okay, so therefore with that, this section is vertical if moment is 0, but the time that we increase the moment m, this plane will rotate, and therefore we have this angle theta. Okay, but of course we have the maximum strain in this region. I'll call this the maximum strain. This is strain, and therefore I can call this as C, meaning the distance from the neutral axis to the top of the beam. Okay, now this is strain epsilon, and this C forms a triangle. So this triangle. So therefore we have the tangent of theta is equal to epsilon divided by C. But remember that in math, okay, the tangent of theta for a very, very small angle is equal to the angle. Okay, and we're talking only a very small angle of rotation of the beam. Otherwise, the beam will crash already and it cannot support any moment anymore. Okay, so with that, therefore, we have theta equal to the strain divided by C. Okay, remember also that from Hooke's law, we have stress equal to strain times the modulus. Okay, and the bending stress, if you recall, is equal to MC divided by I. So this is the MC divided by the section modulus. Okay, so therefore from this equation we can calculate the strain. We can calculate the strain, and that strain is equal to MC over EI. So if I'm going to divide this E here, okay, but remember that theta is equal to strain, which is MC divided by EI divided by C. So that's why this C will cancel, and therefore that theta is equal to M over EI. Okay? So this rotation will tell us the amount of damage. Why? Because the shortcoming of our practice now is what is this EI? Remember that the E of the concrete, say that the code that this is 4,700 squared of F prime C is not true. Because we know that the behavior of concrete, a cylinder concrete, when subjected to this load, the behavior is like this. So that's why in our design, we use this as 0.15 of F prime C, and after that, according to the code, that's the Hognestad model. And then it will drop here to 0.85 of F prime C. So that's why in design, we use this value. And this corresponds to a strain of 0.003. But actually, if you're going to confine the concrete, this strain can be as much as 10 times of the strain of the unconfined concrete. So why are we using E? That is constant. Remember that E is the slope. This is E of the concrete is to 1. But in the code, we are using 4,700 times the square root of F prime C. Number 2, as I've said, I is never I gross. I is never I crack. Okay? And then this I crack is given by the code as, or I effective rather, I effective is given by the code as I crack plus I gross minus I crack times MA divided by, or M crack divided by the moment applied cube. So meaning moment of inertia actually changes with respect to the applied moment. Okay? So basically going back in this slide, the rotation, the rotation of the beam can predict the damage in the beam. So that's actually the concept of, that's how we solve the the amount of damage that was discussed during the inception of the PBD. Because the question of the PBD before was, what if I allow, or what if the damage is only 20% of the total project cost if we're going to build a new building? So we call that the PML, or the probable maximum loss. Okay? Do you have a question? Uh, so there are 4 questions. I just have to read this. Okay. I will just answer this question later on. So these are not as significant, and these questions are not related to our discussion so far. Okay, so I will not. I will now continue to share to you my slides. Okay, so that's actually the basic concept. Before, we just use this equation to derive the slope of the beam, the deflection of the beam. But right now, this equation is not true to calculate the deflection, because as I've said, the stiffness of the beam varies with length as the moment varies with length. Okay? So, performance. The performance of the building is an indicator of how well the structural system supports the need of the user to source earthquake forces. Okay? Why is performance important? Because number one, it will impact life safety. Well, it's already a history of man. The history is already in the history that every time that there's an earthquake, we always expect casualty. And as I've said, these casualties are attributed to the damage of buildings. Okay? So loss of occupancy. So sometimes after an earthquake, we have the tent city. The preparation of our government in the Philippines is, after a very strong earthquake, there are areas assigned to be the source hospital. One is the Veterans Golf Course, if you're part in Quezon City. And then on the west side, if you're in Manila, so you have to go to the uh, Intramuros Golf Course. And if you are in the south of Manila, so you have to go to the Villamor Golf Course. See? Why? Because golf course is an open field. There's no structure that could harm us during strong shaking. The trees most likely will not collapse during a very strong earthquake, because trees are very flexible. Okay? Okay, now next is the repair cost and time of the building. And of course, the downtime of business operations. So there are 5 performance. Actually, there are 6, but I did not include the last one. They're not considered. But the performance of the building is from collapse prevention. So we have reduced safety, the life safety, the damage control, and then the best performance level is the immediate occupancy so far in this document. Okay? Now, the building performance is the limiting damage state for a building, considering structural and non-structural components used in the definition of performance objective. Now, we have to use these different ground motions, no, to analyze our building. So meaning this is the seismic input that we have to use. First is the 50% in 30 years, meaning this is an earthquake with a mean return period of 43 years. And the last is the 2% in 50 years, or the mean return period of 2,475 years. Okay? So the first one is what we call SLE, the 43 years. And the 2,475 years is what we call MCE, or the maximum considered earthquake. Okay? Now, uh, in table 1.3-2, the target reliability or the conditional probability of failure for structural stability caused by earthquake is dependent to the risk category of the building. Okay? And then the conditional probability of failure, for example, of risk category 1 and 2, usually these are houses, okay? Big structures, buildings. Okay? Okay? Again, I took this picture from the Pier 2020 in the US when I attended the conference. The speaker said that, okay, is it acceptable, for example, that we have a risk category 3 and then the conditional probability of failure is 5%? What if we have 100 high-rise building? Is it acceptable to have that 100 buildings and 5 of them will collapse? So that's the question. Huh? So in San Francisco, they have 10,000 buildings. So can you imagine 10,000 buildings? And 5% of that is 50,000. So can we accept that, or rather 5,000? Okay? So also the target reliability or the conditional probability of failure for ordinary or non-critical is even higher. For risk category 4, that's 9%. Typical buildings, I'll say, okay, 1 to 1 and 2 risk category, oh, it's 25%. Meaning there's always one building that will collapse. If there are 4 buildings, so there's still questions about that. Okay. Now going back to the performance or illustrative performance, no, of buildings using the PBD. Okay. Well, I want to discuss this because some people say that, okay, if you use PBD, the building is resilient. Come on. That's a misinterpretation. No? Okay. So resilient building is different from performance-based approach. Now, look at the concrete frame. The concrete frame. Okay, and then the type of that concrete frame is, let's say, the primary element, meaning the main structural system. And if we're going to use the immediate occupancy performance level, meaning the highest performance level, this performance level, look at the damage. Minor cracking, limited yielding, possible at a few locations, and then minor spalling of concrete cover. Okay? So can you imagine if the owner will see his house and then the column reinforcements were exposed already? Do you think the owner will still stay in that house? But to engineers, of course, we understand this. But to a layman, they don't want to see any cracks, even to the walls. Even in walls, they're so afraid about that in my experience. Okay? Now, the acceptance criteria. So we have to divide this acceptance criteria into two. So we have the components and then the actions. Okay? When we say components, this is divided into two. We have the primary component and we have the secondary component. Okay? When we say primary component, this is the component of the building that resists the earthquake force and displacement at the same time. Okay? Meaning when you analyze the building, you have to consider the force and the deformation of that component. Number two is secondary component. In secondary component, you may consider only the deformation, but you may neglect the effect of the force being carried by that secondary component. Okay? So meaning in primary component, we have to consider both force and deformation, But in secondary component, we only have to consider deformation and not the force being carried by that deformation. Now, how do you do that? Well, in a secondary component, what we can do is maybe if we have a column, we can analyze the top of the column is pin and then bottom of the column is also pin, so that we have the lateral deformation of that column, but the force being carried like shear or moment is zero. Okay. Now for actions, we also have two. So we have the force controlled component and we also have the deformation controlled or the force controlled component. And then we have the deformation controlled component. Okay, by the way, if the secondary component will resist significant earthquake force by more than 25%, remember that you have to consider that secondary component as part of the primary component. Okay, so the max is like the requirement of a dual system, that 25% of the frame must be carried by, must resist the earthquake. 25% of the earthquake must go to the frame. In the same way, in secondary component, it's also the baseline is also 25%. Okay. Now, as we've said, PBD is all about rotations. So that's why we have to talk about the rotations, no, of our structural components. So there are three types of curves presented in the ASCE 41. We have type 1, type 2 curve, and then the type 3 curve. Now, in type 1 curve, it is considered as primary component when the D, okay, that D is, look at the type 1 curve, D is the deformation at point 2 in the graph. So we have 0, 0.1, 0 to 1 is elastic, okay? 1 to 3 is plastic. That is plastic, although there's a drop of capacity already. Okay, and then 4 is of course the collapse. Okay, now at 2, that is the maximum deformation D. Okay, if that D is greater than 2G, meaning the deformation of the elastic part, that is called deformation controlled. But if D is less than 2G, then that is what we call a force controlled component. Okay. For secondary component, so any value of D over G is what we call a deformation control. Now, type 2 curve, primary component is when we have the deformation E greater than twice of G, we call that deformation controlled. Otherwise, it is a force controlled. And then the secondary component, so we have F greater than 2G, so we call that the deformation controlled component. Otherwise, it's a force control. And then the last is, normally this is the behavior of a brittle component, like maybe a carbon fiber or a concrete that is retrofitted with carbon fiber, where failure of that element is normally dilapidation of the carbon fiber itself, and yet unless you provide a U-trap. Okay, but usually the limit, the damage is actually demanding of the carbon fiber. So you can use this graph. Okay, so primary component, so everything is force controlled. And then secondary component, so we have if F is greater than twice of G, meaning the elastic deformation, so we call that deformation controlled. Otherwise, it's a force control component. Okay, so basically this is the modeling parameter in table 10-7, modeling parameter and acceptance criteria for of reinforced concrete beam. So we have 4 conditions when the beam is controlled by flexure, beams controlled by shear, and then beams controlled by inadequate development of splicing along the span, or beams controlled by inadequate embedment into the beam column joint. So you can see that A and B are the plastic rotations in radians, and then C is the residual strength. And then of course the acceptance criteria, depending on your performance criteria or the desired performance criteria of the client. So you can choose IO, meaning the immediate occupancy. You can choose LS or the life safety, or you can have the CP or the collapse prevention. So let's say we have condition one, and then we have zero. Uh, I'll just skip this one, okay? So let's say you can see the mouse. So here zero, and then transverse reinforcement is compliant to ECI, and this is the stress ratio. So this is the A, this is the value B, this is C. So if you use a performance criteria of or acceptance criteria of immediate occupancy, then the rotation is limited to 0.01. But if you choose to have a collapse prevention performance criteria, so you can use a 0.05 rotation. Okay. So similarly in column, so we can calculate the value of A, and we can calculate also the value of B. So in these equations, so this is for rectangular column. So there's a different criteria for circular. Okay, so we also have acceptance criteria. So 0.15 of A, or 0.5 of B, or 0.7 of B for collapse prevention. Okay, so but in column normally it's very difficult to do this. So that's why normally in the analysis of column in PBD, what we in our practice, what we normally do is we model the column as a fiber to make it easier to detect the maximum strain in the concrete and maximum strain in the column. Okay, so basically this is one of our 22-story building with existing building. We use PBD to analyze this. So this is the model. Okay, and then remember that as I've said, the D region, meaning the region where it is damaged by shear, normally that is where the maximum rotation also when the end of the beam is connected to the shear wall or to the column. So that rotation must be limited depending on the acceptance criteria that we choose. Okay? So, and of course, part of that beam in between is what we call uh, the B region. And normally that is elastic, so that is actually undamaged during a very strong earthquake. Okay? So in beam, we have, of course, neutral axis. The neutral axis is the transition from compression to tension. But what about in column? Oh, remember that in column, there's no neutral axis. We only have plastic centroid, but the rotation of the column is, if you look at this illustration, we have the pivot point, the horizontal black line, you can see that. So once we have an axial load, it will deform vertically. And after that, if this is subjected to the moment, it will rotate with the moment. Okay, so that rotation will give us that angle theta. Okay, but in column, remember that there's no neutral axis. Okay, so I will pause for a while for questions about the, I can answer questions before I proceed to the topic number 2. Okay. Okay, so there's a question here. Are these applicable for retrofitting design? Yes, yes, yes. Actually, the PBD is for almost all type of structure, either new structure or old structure or retrofitted structure. And it is actually better for a retrofitted structure so that we can actually detect actual damage in the retrofitted structure, because we can detect the rotation in the beam, we can detect the rotation in the column, and so on. Okay. Another question from anonymous attendee. Is it suggestible to use other values of the R factor? The R factor is only used for code-based approach, but in PBD we don't use R, especially if we conduct uh, time history nonlinear analysis. Okay, I'll show you the time history nonlinear analysis. It's R is no longer included here. Okay, I'll try to show you one of our works. So for example, this one. Uh, okay, so this is a 100-year-old building. So we retrofitted this with a dumper. Okay, a viscoelastic damper. So what we did here was to assign moment hinge rotation. So we have this moment hinge rotation. So you can see that from this rotation of the beam, so we have the basic FD relationship. So what is the maximum moment, the yield moment, the ultimate moment, okay, and then the strength loss. So we have deformation capacities, cyclic degradation, okay. So after that, we can create that hinge and provide that with a compound element, okay. So that compound element, so we can have this element where we have the hinge on the left, and then we have this beam that is elastic in the middle, and then we have another hinge on the right. So practically the rotation will only be here. So all this beam here will act as an elastic element, okay. So okay, and then after that we can look at the deformation, so we can plot this and check the displacement, or we can see the limit state whether the beam is immediate occupancy or passes the immediate occupancy requirement or the collapse prevention requirement. Okay. By the way, if you use PBD, take note that this analysis is an event-to-event analysis. So that's why it takes a long time for uh, the computer to process the solution. So you can see that there are red, yellow, magenta, green. Okay, so that's how to do that. Okay, so I will not continue this analysis, but you can see the response. We can plot acceleration and so on. Okay, so uh, okay, so if you have question, you can just post that here. Of course, we will be giving you a certificate. Some of you are asking if we can give certificate. Yes, and also the PowerPoint. We will give you the PowerPoint. Pushover is under PBD. Yeah, a little bit, but we don't use pushover. Any type of structure, we conduct PBD. We put the rotations and we simulate that with the ground motions. Okay, we create our own ground motions every time that we have a project. Okay, is the design of say beam, column, shear wall, and foundation the same for force controlled and deformation controlled? Depends. It depends. Either beam, column, or shear wall. It depends. Take note that even if that is a shear wall, sometimes the failure is not actually due to shear. In tall building, shear wall do not act like a shear element. In tall buildings, it's actually act like a beam, very slender beam. Okay, so it's not like a shear wall for small buildings. So it will depend. So you have to check, as I've said, whether the element is force controlled or deformation controlled. depending on the length of the beam. Take note that if you have a code, the code compliant building, for example, the the beam are defined as those elements in which the length is greater than 4 times the effective depth. Okay. So another question, it seems that PBD is most commonly used in tall building design. Are there some applications of PBD for all types of structures such as bridges? Yes, even bridges right now, the new method is already PBD. Okay. Even small buildings, as I've said, in our practice in the office, we use already PBD even to the smallest buildings that we have, because it's already the trend. Code base uh, well, we know already the shortcomings of the code base approach. Okay. Are these PBD and RBD already being practiced in the Philippines? Yes, in the Philippines, we're doing already a lot of PBD analysis and the RBD analysis, the resilient base analysis. Uh, is the PBD incorporated in the current structural building code? Yes, a lot of building codes already incorporates this, like the New Zealand code, Japan code, and other Euro codes, yeah, other codes all over the world. Uh, Sir, how do we incorporate these designs to value engineering? Value engineering is not about analysis. Value engineering is sometimes just changing the geometry of your structure, because doing such analysis, of course, it should be the same. This is mathematical. If that is what you mean by how do we incorporate this design to, it's not about value engineering. It's about designing the building in the more appropriate way. Because as I've said, in the code base, we just assume that EI are all constant for columns. No matter whether the column will yield or not, whether the column, the moment is zero or not, we still use the same constant EI. We call that the linear analysis. But in PBD, it's not like that. So we get the stiffness in PBD based on the magnitude of the forces that acts in that structural element. Okay. Can we apply the PBD in socialized housing? Yes. Actually, we have socialized housing where we conducted already PBD, but uh, yeah, almost all type of structure. Okay. So I think we can now continue to the resilient based design if there are no other questions. Here's another question. This is angle of rotation in your presentation referring to the torsional angle? No, this is about flexure. It's about because in most of the time in the real world there's no torsion in beam, because this is connected by the diaphragm, the slab itself. So that diaphragm itself prevents torsion in structural element. Except in columns, of course, you have to consider that. Okay. So I think I can now continue my slides. Okay, so what is resilient-based design? Resilient-based design is an approach which identifies and attempts to mitigate all threats that may hinder reoccupancy and functionality objectives through enhanced design of both structural and non-structural components and pre-disaster emergency planning. Okay, a lot of people talk about resiliency, but remember, if there's no buildings that are damaged during a very strong earthquake, we don't need the term resiliency because we have nothing to recover if buildings will not be damaged at all. There will be no casualties, no loss of occupancy, and so on. Okay. Now let's define resiliency. There's a lot of definitions from different sources. So I took this picture from the National Earthquake Engineering Center in San Diego when I attended a conference again this year, just before the lockdown. So there's a lot of definitions from uh, UNSDR, FEMA, NRC, White House, EIE, NERP, and so on. And then the speaker said that, okay, all of this, the resiliency is defined as an attribute of human organizations, okay, primarily about the recovery of the functions or functional recovery of the facility and the people. Sometimes resiliency is measured as a recovery time, meaning how long will the people go back to their houses after a very strong earthquake, or maybe after a minor earthquake like the one that happens in Mindanao before. We went there, we conducted a post-earthquake assessment. We assess those buildings that can be reoccupied. We assess also those buildings that cannot be reoccupied, can be must be abandoned. Okay, and then mitigates shock of natural hazards. Like there are different hazards I have said, but the most destructive hazards most of the time is earthquake and tsunami, which is normally attributed to the effect of an earthquake or called shaking. Okay. Now, functional recovery or FR, another slide from that speaker, he said that, okay, functional recovery is a post-earthquake performance state in which a building is maintained or restored to support the basic intended functions associated with a pre-earthquake use or occupancy. So this is the definition of functional recovery from FEMA NIST. Okay, and then focus on natural hazards, focus on function, not just about safety, attribute of individual buildings, not the organization, and then measured by time. Okay, but the resiliency is different from the code, meaning the code compliance design. So that's why when you conduct an investigation of an existing building, never say that the building is compliant to the code because, uh, or rather safe, because when we say safe, remember, what do we mean by safe? Is it safe from collapse? Is it safe from damage? Is it safe from possible casualty risk? Okay. Now, the resilience is also different from building code adoption. Resiliency is also different from the performance-based design. It's not about the retrofit. It's not about the sustainable or green design, not about the building rating, the emergency planning, good materials, components, or buildings, or improved city services. Okay. the local amendment of the San Francisco General Plan in 2012, 8 years ago, uh, Policy 1.5, it says that new and retrofitted buildings should be built for better seismic compliance than the default level provided by the current building code. Okay? And then in Resilient San Francisco 2016, Initiative 1.8, it says that stakeholders should amend the San Francisco Building Council considering not only basic safety, but also post-disaster usage and occupancy. Okay? Another one is the White House Executive Order. It clearly states in 2016 to achieve a true resilience against earthquakes, new and existing buildings may need to exceed those codes and standards. Agencies are encouraged to consider going beyond the codes and standards set out in this order. So basically, we're going out from the code already. So, but of course, our challenge, no, the challenge to our clients is they just want to comply the code and it's enough. But actually, they don't even ask themselves how much losses will there be in time that this earthquake will happen. Remember, it's not about uh, asking whether the earthquake will occur or not. The question here is when will the earthquake will occur? So meaning we're just waiting for time, and that time can be 1 second, 3 seconds, it could be 10 years, it could be 20 years. And in PVOX, they said that magnitude 7.2 will occur in Metro Manila in our lifetime. Okay? So the Vision 2050 of US San Diego, they say that they plan to have a seismically resilient San Diego. I hope we can also have this in in our different countries. Okay. Uh, so how do we make our building resilient? Okay, I just have this very basic single degree of freedom structure that is subjected to earthquake. Okay, and this earthquake could be north-south, and then east-west direction, and then the vertical direction. So there could be three components of these ground motions that will hit our structure simultaneously. Okay, and of course with that ground motion, the building will continue to oscillate, and that oscillation will depend on the damping characteristic of our structural system. Okay, so the equation of motion, again, I will just show you this again, that the equation of motion of a single degree of freedom is just given by this mass, by this acceleration. So the mass times acceleration will give us the force, we call it inertia force. And then C is the damping coefficient, multiply that by the velocity. So we have the damping force, and also we have the stiffness times displacement. So if you're going to multiply that, then we have the stiffness force. And that is equal to the negative of the mass, multiply that by the ground acceleration. Okay, so if we have a multi-degree of freedom, we can expound this equation and put all of this mass, damping, velocity, and acceleration in matrix form. Okay, so I said this is inertia force, we have damping force, we have the stiffness force, and we have the seismic input. So practically, we're just talking about four components or four parts of the equation that we need to address in order for our building to make it resilient. Remember that this is differential equation. So meaning this is a mathematics, this is an exact science, therefore this is the same anywhere in the world. Okay, so what actually varies here is the most complicated part here actually to estimate is what's the damping. Well, normally the damping we use only 2%, 2.5. If there's high-rise building, some say it's 2% of the critical damping. And then if it's a typical code-based approach, we can use approximately 5% damping ratio. Okay, but actually there are a lot of factors that affect the damping. The damping is not just about the material. It's not just about the geometry. It's also affected by how we attach the non-structural component to our structure. Okay, so that's the damping characteristic or the damping property of the entire system of the building system. But normally we just assume any values like 2 to 5% as I've said. Okay, another main issue here is what is the stiffness? Again, I said the E of concrete is not a constant parameter. It will depend on the magnitude of the load because concrete is never linear. It is a non-linear material. It is a brittle material, so therefore that stiffness case different. Again, we have a different value of I, the moment of inertia. The moment of inertia could be I gross, the moment of inertia could be plastic, or it could be I crack. Okay? And another major concern here is the UG, the ground acceleration, because ground acceleration is very complex. So it's not just enough that we have to get our ground acceleration from the code. So that is why in big structures, we conduct a site-specific study in order to detect the possible ground motions or the wave, no, of the ground that will transmit to our structure, the wave that is coming from the earthquake source, from the epicenter. Okay, so that's why there's also many approaches on how to estimate the seismic input. But typically, if you don't have the site-specific study, according to the code, you can just multiply the value that you get from the code by 1.5, then you can plot your own response spectrum curve. Okay, but that 1.5 could be too much. So if you have a very big structure, that will impact to your design and of course the cost of the design. Okay, so inertia force. How do we make it resilient? How do we make it? How do we minimize? How do we mitigate the impact of this inertia force? Well, it's basic. If you want to make the inertia force smaller, then use a lighter material. That's number one. Okay. So if you are using a masonry structure or non-structural walls, for example, using hollow blocks, don't put mortar. That's basic. Mortar doesn't solve anything. It's just an additional weight to your structure. You can put reinforcements, but maybe you can just put mortar in the reinforcements, or you can use a very thin plaster, or maybe you can use a wall that is lightweight with styrofoam or whatever method that you can use just to make your structure or non-structural component lighter. So that's how to address that. But of course, since that's very simple, we don't need engineers to do that. Okay. Now, dumping is the main problem to engineers. So this is an example of an undamped vibration. Let's say I have this single degree of freedom structure. Okay. And then the damping property is 0. So meaning the value of C is 0. So if you're going to vibrate any object, that building will continue to oscillate with respect to time and it will never stop. Okay? So Of course, we don't want a structure that will never stop oscillating. We want our structure to be at rest, static, no movement. Okay, so if there's a movement, maybe we can allow about 0.15 of G. When you design a tall building or a high-rise building, normally the ground acceleration is around 0.15 of G. Otherwise, the vibration can be felt by the occupants, and of course, they're not comfortable. Okay, now for undamped vibration, meaning you have a very, very low damping property, that oscillation will continue, and therefore it will cause fatigue and continue to damage the cracking and the column or yielding of the rebar, correct? Because the displacement positive and displacement negative is the same, so it will continue to oscillate like that. Then the damage will continue to progress. Okay? But if we're going to use, or we have to dampen the vibration, if we want to stop the vibration, we want the oscillation to stop. Okay, meaning there's a decay of motion from high displacement. Once it reverses, the displacement becomes smaller until the structure will stop. Okay, so that is the damp vibration, and that is the blue lines. Okay, so if we're going to do that, then that's much better, right? So how do we do that now? Well, there are a lot of technologies already available in the market, like this BRB, or the buckling restraint braces, or we have a fluid damper. Okay, so I took these pictures from UC San Diego. So this is UC San Diego have the largest outdoor shaking table in the world. So these are some materials that they are testing in that laboratory. Okay, so we can introduce these devices to minimize the oscillation of our structure. Okay. Another one is we can also use rubber. So what you can see here is the the viscoelastic damper on the left. Okay, so that is just a zero point 0.4 by zero point 0.4 by 0.15 mm thick viscoelastic damper. So that is a damper that is composed of a natural rubber with carbon fiber, with some part of oil and a very fine sand particles. Join them together to improve the property of the rubber. Okay, so this rubber can deform 600%, meaning if we have 10 millimeter thick rubber, it can deform as much as 60 millimeter without damage to the rubber. Okay, so this rubber will now dissipate the seismic energy by introducing the, the damping characteristic of the material itself. So on the right is the picture of a 100-year-old building where we have retrofitted with this viscoelastic damper. So when we conducted the analysis, so we installed the rubber with the color magenta. So these are the locations of the rubber. So that's the strategic locations. And then we have case one, we use conventional retrofitting, and we have case two, we put the rubber, okay? And then when we analyze the structure, so if there's no retrofitting, the drift is as much as 0.03, but with a viscoelastic damper, so it was around 0.02. Okay, but the floor acceleration is also another very important thing, that if we use a steel bracing, the floor acceleration could be as much as 2.5 G, but with a viscoelastic damper, we can have as much as zero point 0.3 G, or about zero point 0.5 of G floor acceleration. Okay, by the way, uh, there are a lot of studies already that a zero point 0.5 G floor acceleration can damage already the ceiling. So if the ceiling will cost around uh, let's say $20 per square meter. So that's a very cheap ceiling in typical construction in the Philippines. Uh, how much losses do you have already if you have that amount of damage just because of that floor acceleration? Not only that, What about the cost of the window? Remember that the cost of the structure is typically 30%. 70% of the total construction cost goes to non-structural component, the wall, the finishes, ceiling, the utilities, and other components of the building. So if this 30% cost of the structure is damaged, meaning the structure is damaged, then you have to replace the entire building. Okay, so those are things that we have to consider. Okay, now using the damper, we were able to reduce as much as 21% of the base shear, but typically if we use a typical brace, it can increase as much as 35% of the base shear. So therefore, we need to retrofit our foundation again, okay, because some reactions will increase with the increase in the lateral strength, and therefore it will absorb more lateral force, okay, and not only that, it will also increase the floor acceleration. So basically, damper can mitigate the impact of an earthquake. So this is the typical drawing, but this is the actual construction of the damper. So this is my team who installed the damper. Okay, so I have 6 men at the site, but there are also other personnel outside the site during in the fabrication area. Okay, and so this is how we install the damper. So the site looks like messy, but some of these materials and equipments are not part of our scope. So because we are just the contractor for design and build for the installation of the damper. Okay. So in Japan, so there are a lot of tall buildings already where they install this viscoelastic damper. The one in the middle, the Proud Tower, I've been there. I was able to see this building with the damper. So this is new. And this is the short video, for uh, how the damper is being used and how it will uh, affect the behavior of the building when subjected to an earthquake.
Japan.
Oops.
Japan, 1995, the Great Hanshin Awaji Earthquake. 2011, the Great East Japan Earthquake. 2013, the Awajishima Earthquake. According to experts, numerous undiscovered active faults lie underneath the Japanese archipelago, meaning a destructive earthquake could occur at any time. Japan is an extremely earthquake-prone nation. No country in the world can be guaranteed earthquake-free. To protect human lives against unexpected earthquakes, there is an urgent need to outfit buildings with earthquake countermeasures. Under a series of new earthquake-resistant standards adopted in 2000 in Japan, buildings must be designed so that a single earthquake with an intensity of strong 6 will not cause them to collapse. However, new standards do not take into account earthquakes with an intensity of 7 or repeated aftershocks. What's more, long period ground motion, extremely slow ground movement, may damage even high-rise buildings located far from a quake's epicenter. Strong winds, for example, as are found in typhoons, can also cause buildings to sway. Perhaps unsurprisingly, Sumitomo Rubber's building dampers have their origins in an extremely earthquake-prone nation, Japan. Sumitomo Rubber's building dampers take advantage of the characteristics of rubber to provide a high level of resistance to repetitive sway caused by large earthquakes, aftershocks, and strong wind. Dampers employ a proprietary technology known as GRAST from Sumitomo Rubber. The the company that developed high damping rubber, which provides an extremely high level of energy absorbing performance. By instantaneously converting kinetic energy into thermal energy, dampers reduce both the magnitude and duration of building sway. Sumitomo rubber dampers feature a compact, space-saving design, and they are compatible with thin columns and girders. Furthermore, Sumitomo Rubber has verified exceptional endurance of this product by carrying out actual size tests designed to simulate a quake with an intensity of 7. What you see here is a graphic reproduction of the results of a quantitative analysis. The building on the right has been fitted with dampers, while the building on the left has not. Yellow areas indicate minor damage from sway, while red areas denote areas of more significant damage. As you can see, the building not fitted with dampers is at risk of serious damage. Sumitomo Rubber's proprietary damping technology, which combines dependable safety with the company's extensive experience in the field, is used in a wide range of structures, including apartment buildings, detached homes, and bridges. Sumitomo Rubber building dampers embody a new earthquake countermeasure that can be used to protect buildings from repetitive sway without regard to siting considerations or cost. Sumitomo Rubber is committed to bringing peace of mind to occupants of buildings worldwide through its exceptional damping technology.
Okay, so that's how damper will uh, contribute to mitigate the impact of an earthquake to our structure. Okay, so it's not only BED. There are a lot of dampers already that is available in the market. So you can integrate that in your design to at least mitigate the damage to our structure. Remember that there are only two things that damage our building due to earthquake. Number one, the drift. So if we can mitigate the drift, then we can mitigate the damage. Number two, the floor acceleration. So if we can also mitigate the floor acceleration, then we can also minimize the damage to the non-structural component and also the structure itself. Okay? Now, the third term is the stiffness force. Okay? So this is given by K times U. So for example, we have single degree of freedom. So the stiffness K is given as 3 times EI divided by L cubed. Okay, so it's easy to use this equation, but remember that E is not constant. Number two, I is not constant. Well, L can be easily computed, okay, but the two parameters EI is the main problem of all of us structural engineers. I said that a confined concrete will behave in a different manner with an unconfined concrete. So in column, for example, remember that we have two types of concrete. One is the concrete inside the core. We can consider that as confined. And the concrete that is outside the core, meaning the concrete cover, can be considered as unconfined. So if you really want to analyze the building more accurately, then you can use a fiber to do that, to analyze that. Okay? So, but the thing here is we have to understand that EI is never constant. Okay? So again, I will repeat and show this video again to you. So we have a very stiff column. Ground acceleration becomes equal to the floor acceleration. But displacement, relative displacement of the mass relative to the ground is 0. And using a flexible column, so we have a 0 acceleration of the mass, but we have a displacement of the mass that is equal to the displacement of the ground. So both of them will damage our structure. The, the rigid structure will damage the content and the non-structural component. The flexible column will damage the column itself and will damage the walls or non-structural components that are attached to it. Okay, so this is an example of a fixed base structure. So when subjected to ground motion, of course, we expect this a lot of shaking in the floor. Okay, and then of course we have a flexible base. Okay, I call this a flexible base. So if the structure is supported by a flexible column, then the structure can be detached from the damaging effect of the horizontal ground motion. Okay, so this is what we have to avoid, the damaging effect of the horizontal ground motion. And to do that, simultaneously minimizing the drift and the floor acceleration is to provide this flexible base. Okay, so therefore it will reduce the story drift, it will reduce the floor acceleration, and as I've said, less damage will occur in our building. Okay, so that flexible base is typically called the base isolator, but I will call this seismic isolation because right now the practice worldwide is uh, the isolation is not placed at the base anymore. There are isolations in which they put in a strategic location. It's not necessarily at the base. For example, you have an existing building already and you want to isolate uh, the mid-story above that floor because, for example, you don't want the mid-story because that is an office. You have to minimize floor acceleration, minimize the drift, and so on. And for the lower structure, you want also to minimize the forces, so you can isolate the two parts of the building together. Okay, so that is called inter-story isolation. So that's why I want to call this a seismic isolator or a seismic isolation, because I repeat, you can put this anywhere in the building. Okay, and it doesn't have to have the same isolation plane. It can have a step isolation plane, or you can just have horizontal isolation plane. It depends on the requirement of a specific building. Okay, so the concept of the seismic isolation is to decouple the structure from the effect of ground motion. Okay, uh, the concentration of large deformation at the isolation level. So, so we can concentrate the deformation in the isolator or the seismic isolation. And then number three is the building will just act as a rigid body that will just move along with the ground motion. Okay, and finally, the flexible base isolator will filter the high range of strong ground motion frequencies to smaller one. So that is why if we use a seismic isolator, the response of the building above the isolation plane becomes very, very small. And most of the time, that response of the isolation of the isolated building is just around 90% than the typical code base. So 90% is really too much reduction in the response of the building. Okay? So this is the basic concept. So if you're going to look at this, I just took this simple video from Google. So if you look at the left building, so this is subjected too much to a seismic oscillation, and therefore it generates a lot of drift and floor acceleration. Whereas if you're going to concentrate a soft or flexible support to the structure at the base, then that structure will just act as solid or a rigid body while the ground is moving. Okay? So that's the concept. So the basic feature of the seismic isolation is the lateral flexibility. So meaning the lateral flexibility of the isolator itself. But of course, it must be able to support the gravity load, okay, without bulging. Number two, it must be strong to support the weight of the structure from dead load, live load, and of course the effect of overturning due to earthquake. And then period shifting, meaning from a short period structure, we can always make a long period structure. Okay? And of course, the damping and energy dissipation. So we can improve the damping from typically a building with without dumping additional damping property from any devices. Typically, it's just around 5%. But I said it can range from 2 to 16% in actual measurements of damping. But with a seismic isolator, we can improve the damping property of the system to as much as 30%. So meaning the oscillation might be just 2 times rather than without a damping property, the oscillation will continue. Okay? So this is the response spectrum curve or response spectrum acceleration. Okay, so the vertical could be pseudo spectral acceleration, or we can convert that into a seismic coefficient. And then the horizontal axis is the period of vibration of the structure. So typically that's the RSA of our code. Okay. So and if we have a fixed base for typical buildings, normally the period range of our buildings is normally the period of the building is taken as zero point 0.1 times the number of floors. No? So if we have, for example, 10-story, the period of vibration should be 1 second, but that's far from reality. But there are provisions in the code where we are allowed to calculate the period of vibration as zero point 0.1 times the number of floors. So rough estimate. But to design the building, to design the structural component, we have to use the period of vibration as TB, meaning this is the period of vibration based on the stiffness and the mass. Okay, but that TB should not be more than 1.3 times TA. If you recall that, TA is C sub T times the height of the building exponent X. X can be 0.75. In our code, it's 0.75 or 3/4. But in the new code, it ranges from 0.75 to higher than that. Okay, so typically that's the period of vibration. But if you're going to elongate, you're going to prolong the period of vibration. Okay, so prolonging the period of vibration will give us. By the way, so we with the damping property of the isolator, we can reduce the pseudo spectral acceleration. Okay, so the higher the damping, the higher the reduction in the spectral acceleration. And with that, therefore, we can shift the period of vibration from left to right, meaning the longer the period, what will happen? The longer the period, meaning the shifting the period from smaller to longer, then we have this reduction in the spectral acceleration. So you can see that there's a lot of reduction in the spectral acceleration. So multiplying that spectral acceleration by the total mass, if you have single degree of freedom, then that's already the equivalent earthquake load. Okay, so that's actually the basic concept of the seismic isolations. No? So There are a lot of buildings already constructed with seismic isolators in Japan. In the 2015 report, they already have 7,800 buildings. The biggest seismically isolated building right now is in the US, the Apple Center. Okay, and then tallest building so far is the Nakonashima Festival Tower. So that is in Japan, where they put the isolator at the ninth floor. Anyway, so this is a basic concept. Shifting of the period, and number two, increasing the damping will reduce the spectral acceleration. So therefore, with that, reduction in spectral acceleration will therefore reduce the response of the building. Okay, and reduction in damping will reduce the oscillation, and with that, it will decrease the impact of drift and acceleration that, as I've said, the cause or the culprit of damage in our structures. Okay, so looking at this graph, I took this figure from the book in dynamics of Chopra. Okay, so you have to read that book. That's a very good book in dynamics. Okay, you can see that for a fixed base structure, mode 1 up to mode 5, we call that the structural mode. So mode 1 is just bending in one direction. Mode 2 could be like this. So then change the frequency. So you have mode 5. Okay. But if we're going to put an isolator or seismic isolator, the mode 1 is just the deflection of the isolator itself, assuming that the structure above the isolator as a rigid body. Okay, so we call that the isolation mode. Now, the second mode is what we call the structural mode. If you look at the fixed base, the mode 1 of fixed base and the mode 2 of base isolated structure is the same. So meaning there's already a shifting. So meaning if the first mode will get the higher period of vibration and a higher mass participation factor, then the rest of the mode will be irrelevant. So meaning we need less number of modes in base isolated structure than a fixed base structure, because the deformation was already absorbed by the isolator during the first mode. Okay? So the modes here, the so far the main problem about these modes is, even in the code-based approach, is that we are assuming that even in mode 1, we use a constant AI, okay? Using the linear static analysis or linear dynamic analysis. Even if you use linear time history analysis, the main problem here is this. This is another research. No? There's a lot of research coming out about the shortcoming of this combination of modes. Number one, in mode 1, the drift is going to the right, all right? So therefore, the bottom part of the structure has yielded already. But the top part of the building has not yielded. So therefore, EI at the bottom is not the same as the EI at the top. Okay? Now, in second mode of a fixed base structure, you can see that the bottom part of the structure has yielded, assuming yielded, okay? And almost 1/3 at the top, or 2/3 from the bottom of mode 2, the mode shape is from the vertical axis of the original position of the building. So meaning it could be concluded that the EI of that part of the frame is I gross. Okay? And every mode, we get the period. Remember that the period of vibration is 2 pi divided by the natural frequency. And the natural frequency is the square root of the stiffness over mass. You remember that? I will repeat. The natural frequency is the square root of stiffness over mass. Now, mass will not change, but stiffness will change with time. Correct? So, but of course, right now, these are things that we need to be addressed in the future. But at least we know that there's something that we need to improve in the future practice of structural engineering. Okay, but there are some methods now. But in typical software that you can use, you can just combine all these modes using SRSS or square root of sum of the square, or you can combine this with CQC, combined quadratic combination, or you can just combine this absolute or any other combinations. Okay, and after we combine all these modes, then we can check now the design base shear and distribute that design base shear based on the different combinations of the modes as well. Okay, so those are shortcomings in this approach, but as I've said, in the future we can address that. But at the moment, we need to build our buildings even without those research. So that is why let's use this very important tool right now in order to design buildings. Okay, or to continue designing our buildings. Okay, so as I've said, this is the isolation mode, and this is the structural mode, and this is the yeah, isolation mode. Okay, now, so that's about stiffness. So we learned that there are a lot of things that we need to address in the stiffness of the building, from E to I to mode shapes. Okay, so the last thing, the last component, no, of from the differential equation of motions, no, of our building is the seismic input. Okay, so this is a very challenging job to earthquake engineers and of course to all of us structural engineers. Okay, so again, I took this picture from our conference in San Diego this year. So the speaker said that, okay, in 2022 there's coming up another study being conducted about the ground motions, because they realized that there are earthquakes, smaller earthquake magnitudes that are very damaging, but there are also very strong magnitude earthquake that are not damaging. And then they consolidated a lot of earthquake records from all over the world, and then they say that, oh, we cannot just adapt this ground motion, multiply this by FA or FD in order to address the soil characteristic of the specific site, and then we can already use this ground motion. No, they were able to find out that the ground motions are really unique. And as I've said, they even found out there are smaller magnitude earthquake that are more damaging than of the same structure. I'm talking about the same structure. Uh, and strong magnitude earthquake that are less damaging to the same type of structure. Okay, but typically we understood before that when we say earthquake, long period earthquake is more damaging to tall building. Short period earthquake are more damaging to short building. Okay, so that's what we understood before. Well, until now that's quite correct, but we need to modify something about those informations. Okay, so I will not discuss much about the ground motion, but if you don't have the source about this, you can just use first from the code, multiply that by 1.5, you can already get the MCE, or the maximum considered earthquake. Because it will cost you a lot to create your own ground motions. But in tall buildings, we need to have that. Okay, we have to have our site-specific study. Okay, so this is the time histories that we derive in one of our project. You see this blue, yellow, and green. Okay, so by the way, we use CMS or uh, conditional mean spectrum. Okay, so you can see that the three earthquakes, the green, yellow, and the blue, are most damaging. So these are earthquake for the 0.2 second. No? And then we also have earthquakes beyond that. We have the 1 second earthquake and the 3 second earthquake. So we have to test all these earthquake records to design tall buildings just to make sure which among the nine ground motions are most damaging. Okay, so in the ASCE, if you conduct time history analysis, nonlinear analysis, it is now required that you have to have at least 11 ground motions. Okay, but if you have an isolated buildings or any buildings with dampers, uh, only 7 ground motions are required. Okay, now the application of by the way, I think I have to pause for a while for at least 10 minutes for us to have a break. So we will come back in 10 minutes. So around 3:36. Okay, so please pause for a while and uh, come back if you want to go to the toilet or have some drinks. Okay. Okay, can we continue? Okay, so this is now the application of seismic isolation all over the world. Previously, they say that, okay, highly effective for low to medium rise buildings. The isolation is only effective for mid-rise up to low-rise to mid-rise buildings. And then the number of base isolated structures is increasing yearly. But right now, we already found out that seismic isolation is even much effective in tall buildings. No? So this is the graph on the left. So this is one of the paper presented during the World Conference on Earthquake Engineering in 2015. They reported that in Japan they have 6,600, but right now it's already 7,800. Okay, so that's the updated data. No? And then the application of seismic isolation in tall buildings. So far we have the LA City Hall. So this is a 32-story and 138 meters tall. So this is from the ground. But the LA City Hall, they retrofitted this building after the Northridge earthquake happens. No? And then the Thousand Tower in Japan. So this is 135 meters. The Gondang Garam Tower in Indonesia, the G2 building in Japan, and then the Sendai building in Japan. Okay, but not part in this table is the Nakunashima Festival, which is so far the tallest building with inter-story isolation. So they put the isolation at the 9th floor. Okay. So this is the latest from the July 2015 report uh, of the golden standard of seismic protection. So in the US, they already have 500 buildings. In Japan, 7,800. In Canada, Chile, Colombia, Mexico, New Zealand, and in China, 4,000. But China is fast growing in terms of application of seismic isolation already. So overall, in 2015, we have around 13,000 buildings already. Okay. So Japan and Italy, so they have a lot of buildings that are in progress and also designed, but still very few were completed during the 2015 report. Okay, so this is the LA City Hall. So this is the base isolator that they put in the column. So you can see that there are two isolators in one columns, one column, no? And then they join them together. So LA City Hall is 138 meters tall, but this building is actually on a step, no? So this is sloping. So we enter from the front and then we go back at the back. I think there are around 3 floors difference. So they put sliders, floor sliders around the building because it's the tower and the podium that were isolated. So meaning everything was isolated in the LA City Hall. Okay, so Sendai MT building. So this is an 18-story building in Japan. Uh, in their analysis, they were able to reduce the story drift to as much as 0.002. Okay, so that is for level 2. And then for level 3, the drift is just around 0.003. Okay, so the Sendai building was also hit by an earthquake already. So it was actually tested. So they recorded the floor acceleration. Okay, and then the record is quite different from their simulation, but uh, maybe there are some effects of the non-structural components on how it was attached for the structural model itself. So that's why there's a small difference between the recorded and the uh, simulation. Okay. Now the Thousand Tower is another 41 story with a base isolator. This is in Kawasaki City. The height is 143 meters, but the isolation was placed just above the ground floor, and then this building was on pile. So the based on the paper that was presented for this building, it was noted that the response of the base isolated structure is very small, around 0.005 as compared to the non-isolated building, which is more than twice. So, okay. So another building in Jakarta. So this is the first isolated building in Indonesia. So this is a 25 story, and the total height is 87.5 meters. So they plotted fully operational FO and then immediate occupancy IO, the life safety and the collapse prevention performance level. So they noted that the interstory drift for immediate occupancy is around 0.5%. And then for fully operational, so they use around 0.2% interstory drift. Okay. Again, you can see the difference between the blue line is the isolated, and then the fixed base is the green uh, uh, for the story drift. Okay, so this is another one, the NOAA Capitol building. So this is a twin tower, but it was only the tower that was isolated, and then the podium is not isolated. So you can see that both the drift and acceleration were reduced significantly. In typical code-based analysis, as I've mentioned, the dilemma is how to minimize the drift and the story drift simultaneously. But with the isolator, we can see from the responses of the simulations that both drift and floor acceleration can be mitigated simultaneously. So basically, that's the best solution so far. Okay, so this is the response of the Nakunashima Festival Tower. So far this is the tallest in terms of height. Okay, so this is in Osaka, Japan, and then they put the isolator at the ninth floor because the ninth floor and below they provided only column around the perimeter of the building. Okay, so it's only around the perimeter of the building because they have the uh, it's a festival tower, so they have a big auditorium. Okay, and then above that ninth floor, they put a mega truss. Okay, so this blue one you can see from the section. That blue one is the mega truss, and then that mega truss supports the tower, and the isolation is below the mega truss. Okay, so you can see that also the responses of the building is very very far away the from the limit of the drift angle that they use in their design, the 1/150 drift angle. Okay, so in also in Japan, the Shidom Sumitomo building, so they also put isolator here, but the isolation is again above the atrium. Okay, so that's why we're now changing the name from base isolator to seismic isolation. And then the 35-story tower in Korea. So these are so far applications, no, of base isolated uh, of base isolation, no, in buildings. So this is the picture where I took from the UC San Diego. This is the largest testing machine. So they tested a 6-story building here. Okay, so these are the isolators. By the way, typically there are two types of seismic isolation, but originally, historically, if you're going to read a lot of articles about isolation, seismic isolation before was invented by a medical doctor. So where he used talc. Okay, it's like a clay, and then they put the structure above the clay, so that the ground during an earthquake, the building will just slide. Okay, and then after that, another idea came out, and then they used the rubber, but the rubber will bulge. So therefore, to prevent that bulging, what they did was to provide a glass blocks around the rubber, so that during earthquake, the glass blocks will just break, and therefore the rubber will now activate in the as a soft material to resist the lateral force. Okay, but of course there will be a vertical movement. But right now, this technology is maybe I can say a fully developed technology. So we now have different types of seismic isolators. We have on uh, on your left is the photo of a friction pendulum system. Okay, friction pendulum system is just composed of metals, and then there's sliding metals inside. So there are different types of friction pendulum systems. So we have triple friction pendulum, double, and many other types. So some of them are sliders like that. So it's just a plain surface of the metal, so that when there's an earthquake, the column will just slide from the ground. Okay, but of course, when you use a slider, you have to use other type of isolators that will restore the building from its original position. Okay, so there is a requirement for the restoring force, what we call restoring force, so that there will be no residual deformations in the isolators after the earthquake. Okay, now on your right, that's the picture of a rubber isolator. So in a rubber isolator or natural rubber, there are also many types. We have lead core rubber, so meaning there's a lead in the middle of the isolator, and that lead will improve the damping characteristic of the system, meaning the rubber and the lead will prevent the the structure from further oscillation. Okay, but there is also a pure natural rubber that you can use for isolation, and there is also a high damping rubber that you can use. There are also sliders using the rubber. Okay, now, but of course this technology is quite developed already, and they know that this excuse me, this rubber will bulge upon the application of the vertical load. So the manufacturer, what they did was to put a very thin layer of metal, so that excuse me, that metal ranges from 1 mm to around 1.5 mm, and then the thickness of the rubber will also depend on the design. So it can range from 15 millimeter to 30 millimeter, so that the bulging of the rubber will just be localized. Because, for example, if we have a 1 meter thick rubber, bulging is too much. So to localize that bulging, small bulging per layer of the rubber, they put a very thin steel plate to prevent the expansion, lateral expansion uh, of the system. So that, number one, it can resist a higher vertical load. Okay, resist the higher vertical load, and of course the maybe the vulcanization will not also be that difficult, because vulcanizing a very thin rubber will also can also be a problem. Okay, so this is a simple video that I took from the website of UC Santiago.
Check out and subscribe to our YouTube original channel, UCTV Prime, available only on YouTube. May 15, 2012. The culmination of the largest and most complex seismic test ever conducted. A project comprised of 13 earthquake motions and 6 fire tests. Now, this specially designed and instrumented building is about to experience one of the most severe earthquake motions ever recorded. Why? Back in 1971, a moderate magnitude 6.6 earthquake struck Southern California with devastating consequences. It was like a harder shake and a harder shake. The crunching to me was like a roar. I heard a lot of rumble. Maybe it was the earth, maybe it was what was falling. All the false ceilings, they're coming down. And is there going to be a roof behind it? Closets were falling onto beds. Furniture was moving around, glass breaking, people yelling. Seconds later, you felt the sensation of going down. We used to be on the second floor, and we had become the first floor. Fortunately, at 6 a.m., the ground floor offices of this building at the Olive View Medical Center in Sylmar were vacant. However, the 800-bed main hospital building, occupied by over 600 patients at the time, suffered severe damage and narrowly avoided collapse. Unfortunately, nearby Olive View, 4 of the San Fernando Veterans Administration Medical Center's oldest buildings collapsed catastrophically, claiming 49 lives and severely impacting emergency services. It's important to realize that the day will come when we will have a major earthquake in our state, and it will significantly disrupt an entire region of the state. As a result of that, we need the hospitals to be physically strong enough, inside and out, to be able to withstand the shaking and continue functioning. To achieve these goals, the National Science Foundation and the California Seismic Safety Commission brought together an extraordinary consortium of industry, scientists, engineers, and designers from across the country and around the world on this project. Floor by floor, 5 stories in all, from the foundation to the massive air conditioning equipment on the roof, from the structural frame to the healthcare equipment that eventually fills the building. The structure is specially designed to meet the intent of current building code requirements. Over a 1-month period, the building was subjected to ground motions created by one of the most unique facilities on Earth, the Nice UCSD Large High Performance Outdoor Shake Table that is managed by the National Science Foundation at UC San Diego's Engelkirk Structural Engineering Center. After days of testing with a variety of ground motions, the team is ready to conduct a crucial sequence that will directly test current codes and practices. First in the sequence, a near design level earthquake event. This is a test using an earthquake motion that occurs approximately every 475 years, with the expectation that the hospital building will remain functional. The researchers use a record from the 7.9 Denali earthquake of 2002. The Denali quake is a phenomenal record. Over 2 minutes of violent shaking. The images speak to the devastating power of this quake. For the first time ever, this test has shown how both structural and non-structural designs and codes hold up to a severe design level earthquake. Bob Bachman, an expert instrumental in the development of many existing seismic codes, comments on the preliminary observations.
We're very pleased with the way it's performing. There's just limited damage to the building structure right now. And so it could actually take a lot more motion before it would consider collapsing.
Finally, it is time for the ultimate test, a motion that exceeds a maximum credible earthquake event. This is an earthquake that happens approximately every 2,500 years. Codes and designs for this motion have the performance expectation that the building will not collapse, but will lose functions and be severely damaged beyond repair.
10, 9, 8, 7, 6, 5, 4, 3,
The violence and severity of the quake is clear. This would be a frightening experience not soon forgotten. Close inspection reveals that the building suffers irreparable damage.
I think this building in a real world situation would be condemned.
But the building has done its duty. It bent and cracked, but did not collapse.
It satisfied the design objective that the structural system should still stand, even though maybe close to collapse, but still stand. It resisted, so it's a success.
In the weeks prior to conducting these ultimately damaging tests, the team had tested the building on seismic isolators in order to directly compare the effects of seismic isolation on the performance of non-structural elements. In a test using a record from the magnitude 8 Ica, Peru earthquake of 2007, the effect of base isolation becomes obvious. As the table displaces, the isolators provide elastic joints between the earth and the structure, dramatically attenuating the accelerations that are transmitted to the building. The contrast with the motions in the other tests is clear. With isolators, the building slides back and forth smoothly and easily. While objects and fixtures shift, the violent displacements and the destruction they wrought upon the building in the fixed foundation tests do not occur. 90% or so of the displacement that actually was imparted on the building was absorbed by the isolator. And so the result is relatively minimal impact on the contents and the non-structural elements in the building. The hospital could remain functioning. The patients would be saved. The equipment, critical support equipment would remain functioning. The electrical system in this building remained functioning. So life support equipment for patients would remain functioning. That's essential. The elevator remained functioning. The stairs were completely intact. So paths of egress through the building remained functional. So that's a success. The future? Downtown Los Angeles. Like any other major urban center in California, over 500 buildings exceeding 5 stories, many exceeding 10 or more, hundreds of elevators. Within about 5 miles, there are 7 hospitals with 911 emergency rooms and intensive care facilities. 3 of those, trauma centers. On any day, over 2 million people are going about their business here. It's 1 p.m., 9 a.m., 6 p.m. Will it happen in 2,500 years? 500 years? Or today? For certain, it will. And when it does, will our hospitals have the resilience to keep on operating just when we will need them most? And what remains to be done so that they can?
Okay, so that's actually the tallest building ever tested in the laboratory with isolator, and it works. So there are also some existing buildings that were actually tested already with actual ground shaking of an earthquake, but again, it works. So meaning our simulations could be more realistically
Check out and
uh, achieved when we design isolator. Okay, now this is one of our project. So this is actually a 45-story, and so far this would be the tallest building in the world once this building is constructed. So this is a building with isolators at the 4th floor. So again, it's a different it's a different design. So it's not just a base isolator, but an inter-story isolation, because because of 2 things. So we want to construct this building without columns at all. So meaning wall system above the isolator, and then we have columns below the isolator. So we were able to estimate the amount of drift, story drift, and floor acceleration, and we're able to achieve that, our desired performance level. So actually, this building is complies with the requirement of a fully operational in the event of a very strong earthquake. So basically, these are the results of the analysis. Period is about 5, and then mass participation factor, we also plotted that. And then these are the floor accelerations. By the way, we use the conditional mean spectrum for this analysis. So what we did is we have 3 groups of earthquake records for the 0.2 second. We also have 3 groups of ground motions for a 1 second period. And then we also have 3 groups of ground motions for the 3 second period. So these are the floor acceleration, and you can see the average actually is around 0.2. As I've said, the ceiling can be damaged already by 0.5 G floor acceleration. So our acceleration is way, way below that. So therefore, we expect that even ceiling will not be damaged. Okay. So this is the floor acceleration along Y. So it's almost the same thing. And also the interstory drift is very, very small. So practically the structure above the isolation will just act as a rigid body, but the deformation, the first mode will be activated by the deformation of the base isolator of the 4th floor. So with that, the rest of the floors above the isolator can maintain their very low frequency, and therefore everything is protected above the isolator. Okay, so This is the storage here, and then I did not plot all the rest of the result, but as I have said, we were able to achieve a very, very small story drift. We were able to achieve a very low base shear. The base shear is even less than the minimum requirement of the code. But even if we're going to adopt the minimum requirement of the code above the isolator, the results still very low. Okay. The only downside of that design is that below the isolator, we still expect as much as 2.5 G floor acceleration. So therefore, we have to provide special detailing for ceilings and other utilities in order to prevent damage to that 2.5 G floor acceleration. But the columns below and the beams below the isolator, we were able to achieve a strain of 0.001 or even less than 0.002, meaning the concrete will not crash at all. So the concrete is within the elastic range. All the rebars are all within the elastic range. So therefore, the structural system itself, the columns and the beams below the isolator are well protected because the inertial forces above the isolator were already reduced. So these are some of our projects with isolators and dampers. So from big to small buildings, so these are the projects that we are doing so far. We're going to cut an existing column of a 6-story building and insert that isolator. So we have all the equipments to do this. Okay. Now, detailed earthquake information or performance information will of course achieve a more resilient building that has less damage and improve the functionality after an earthquake, as well as reduce environmental impacts. Because you can imagine if we have to condemn a 140-story building, um, how much impact would it be in the environment by again using another amount of steel, bulk volume of steel and concrete. Okay. Now, it better understand and control their risk exposure and reduce the uncertainty, increase the value of the property at the time of the sale. So meaning the ceiling point here is if we have a resilient building, we can even increase the rent of our structures. So this can be integrated in the cost already, the selling price of the building or even the rental cost of the building. Okay, and then thoroughly evaluate choices when considering purchase or renovation alternatives. Most of the time, in my experience, the owner wants to renovate all the finishes, the fit outs, but they don't even care about what will happen to the structure. Uh, and then when we conduct the structural investigation, we found out that the building is about to collapse. We have a very weak concrete. We have a very far spacing of the ties and so on and so forth. So this becomes a big issue. But of course, what we normally do with that type of retrofitting is we do this proactive approach. Instead of resisting the earthquake, we dissipate the earthquake with all these seismic devices. Okay. Well, we can uh, gain better confidence and peace of mind from having clearly defined seismic performance goals and plan for achieving them. So these are actually the advantage of using a resilient-based approach. Okay. Now, I just took this picture again from one of the conference in the US. One of the speakers say that, okay, what does the future hold? What's the prediction ability of the human species? Some of them, I want to stay in Mars, so they were able to go to the Mars. They were able to create rocket. They were able to create cars without fuel, so they use battery operated cars. Before, some say that in order for you to see other person kilometers away from you, you need a telescope. But right now, we have FaceTime. Before, we conduct lecture in a classroom, but right now, we conduct lecture online. So there's also a future in structural engineering. As I've said, the base year of the code that is between point 1 to point 2 has been used already by the code for more than 100 years. What changes in the code is only the detailing of the reinforcements most of the time. So we use a lot of confinement just to make sure that the building will not collapse, but still suffer a lot of damage. So I hope that in the future, these anti-seismic devices like damper or isolator is now part of our design, and forget about the old practice that we are doing uh, in our practice. Okay. So as Peter Drucker said, if you want something new, stop doing something that is old. Okay. Thank you very much. And I would like to announce that, by the way, we still have our question and answer later. But before I do that, I would like to announce that we have our upcoming pre-earthquake assessment of buildings this 22 of May. I think this is Friday. So tier 1 is the pre-earthquake assessment of building, in which you just need the as-built plan, you need a calculator on paper for you whether to check, for you to check whether the building is compliant or not compliant. So if the building is not compliant, then you have to go to tier 2, and then if not compliant with the tier 2, that's now where you have to use the tier 3 or the more detailed analysis. Okay? So I want to read these questions. You can post questions. What is the best starting book, code, or reference to learn PBD and non-linearity concept? Well, there's a lot of books already available in the internet. There are books that you can buy, but I think first thing that you have to read is about ATC, uh, ATC 40-1, and how so that you have an overview, the background, how the PBD innovates, okay, and what are the shortcomings of PBD, why we still have the RBD or the resilient based design. Okay. Another question is, I would like to ask what website can we get seismic time history data, probably in Cebu or Visayas? Well, it's not just about, by the way, it's not just about getting an earthquake record and then use that in your analysis, okay? You have to consider a lot of things, the type of fault line, whether that is strike, is slip, the fault line, the source, how far is it, the type of the soil, and many other factors that you need to correlate before you can have the uh, ground motion to be used in your analysis. In our practice, we're still we are conducting micro tremor analysis. So we have a device that we triangulate the area of the specific site and then detect the ground motion so that we can correlate that ground motion into the time stream that we will use in our analysis. Okay. For seismic isolation, a question from Engineer Camo. For seismic isolation, what is the connection of rubber and steel base plate so that no slipping will occur? You just have to bolt this. You just have to put an anchor. And take note that this anchor doesn't have to be compliant to the ductility requirement of the code. Because as I've said, we can reduce as much as 90% of the seismic energy. Okay, it's just a bolted connection. Next year, supposedly this year we have a resilient base conference, the international conference on resilient base approach. But of course, because of the pandemic, we were not able to push through that conference. But next year, we will post through the same conference, and then part of that conference is to conduct a site visit of our projects with base isolators and with damper, so that you can see how these anti-seismic devices are installed. So wait for that. Please wait for that. We will just announce that by next year, probably That will be in April. Okay. Another question. Is it safe to say that isolators can increase the design life of a building structure? Yes. Well, actually, the design life of the structure depends on the maintenance. No? Most of the time, there are a lot of degradation in the structure because of poor maintenance. Why isolators can protect our building? Well, because even to a moderate magnitude earthquake, we can allow energy dissipation in the isolators. Okay, but of course, when you design the isolators, make sure that you comply the restoring force of the code. That's 0.025 of the total weight. That's the restoring force that you need. And uh, number two, that isolator should not activate during very small ground shaking. Okay, so there's no activation of the ground shaking, and of course, due to wind load, the the base isolator should not activate due to wind load. Anyway, either dead load, live load, or wind load, we design our structures and all the structural components to be within elastic range, so we don't have to worry about that. What we need to worry is the earthquake analysis, because in earthquake analysis, we allow the structure itself as a fuse to dissipate the earthquake energy, and with that, we allow damages in our structure. Okay? um, Another question. If I may ask, did you do bounding analysis for the isolation and the bounding maybe? Yes, it should be considered. Yeah, it should be considered. Uh, if you have, for example, adjacent structure, you have to check the pounding. No, so you have to calculate what's the maximum story displacement because there might be some pounding to the adjacent structure. In RBD, are we still need to check irregularities? Well, irregularities is only for the code because, as I've said, in the code we use the inelastic seismic energy. We allow too much drift. We allow too much acceleration. In RBD, if there's no earthquake above the isolator already, then these irregularities will not contribute to the response of the structure. You know why? Because as I've said, in the code-based approach, we are using linear analysis. Although in the code, there's a non-linear time history analysis already, but the point here is we allow these materials to yield beyond the elastic. So in RBD, if everything is elastic, then we don't even have confinement. We don't need confinement in column. We don't need confinement in beams. We'll go back to the original design using work stress and so on and so forth. Okay, because the earthquake energy is already being dissipated by the anti-seismic devices. Okay. Okay. What are the challenges in the application of PBD? Well, the challenges in PBD right now is, as I've said, even if you design PBD, take note, it does not consider the floor acceleration. It's just all about the rotation. In the code, there's no requirement for in section in ASC 421. It's just all about the rotation of the beam to estimate the damage in the beam, the column, whether that is IO or collapse prevention. So that's the shortcoming so far. That's why in FEMA right now, 58, P58, they already have the next generation PBD, where you really have to estimate the extent of damage, not only of the structure, but the non-structural component, including the content of the building. Okay, and also the shortcoming of RBD right now is that we as structural engineer, when we specify the properties of the isolator in our design, sometimes I felt that some of the manufacturer cannot really do it. So, and right now, if since the demand still, there's still very few demands on the isolators, and they have to do specific mold for that isolators based on your requirement. so the cost becomes a little bit higher. Okay, but if the manufacturer will already have a lot of molds in their factory, then that cost might go down. But in terms of design, I think it's the final destination no, of being a structural engineer to design all buildings using the resilient-based approach. A lot of people right now, non-technical people, are talking about resiliency. But this resilient approach, as I've said, is that they just look for people to evacuate, and then they call that resilient already. It's not all about that. And structural engineering perspective or point of view, we have to maintain that supports of the non-structural components and the content of the building and the occupants, which is the structure, must be able to maintain their function even before or even after the earthquake will occur. So that is all about, that is what a resilient based design is. Okay. Another question. This one is a good question. Base isolation can resist great tension from large overturning moment? No. So that's why this is another thing that you have to consider when you design a base isolator. Because the isolator is very weak in tension. Now, if you use, for example, a friction pendulum system, there's no tensile capacity. But if you use the rubber, either that's a high damping rubber, you have to limit the tension. Normally, some suppliers say that maximum tension is only 1 megapascal. Because after that, the rubber is subjected to tension, there will be some cavitations already in the rubber. If you increase the tension further, that cavitation will increase until the tensile strength of the rubber becomes zero. So that becomes a very big issue. So that's why when you design, make sure that there's no too much torsion above the isolation, because that too much torsion will also cause torsion and large deformation at extremes locations of the isolators. So a lot of things to consider in the design of isolation. No? Not only that. Okay. Another question: does the rubber degrade over time? Well, I can say that it's not, because the factory that I went to, one of my partner in Japan, they tested the rubber, accelerated testing in the laboratory, and they found out that there's only around 5% of the rubber that were damaged due to oxidation for over 80 years. So can you imagine that? 80 years span. So there's a very, very small damage in the rubber. And when this rubber is constructed, there's a structural rubber inside, and then there's a non-structural rubber outside the perimeter to protect the structural rubber. So that is how it is being fabricated. Okay. Another question from Engineer Conserman. Uh, in retrofitting installation isolators by cutting a column, is there a structural effect above it, or how about the termination of column being cut? Well, as I've said, we have projects that we will cut all the columns, and then we have a jack. I bought it from abroad, and one jack is 100 tons, so I have 4 jacks. So it can support as much as 4,000 kilonewtons. So that's about the reaction of a 10-story building. So we can do that. Okay, I will just show you some pictures or site visit maybe next year when we have our international conference on hybrid structural engineering. So please watch out for that. Okay. Uh, how much cost in percentage increase using base isolator using the traditional fixed base? Well, actually, there's a very, very minimal cost difference, almost equal. Why? Because using a code base, but it's not about comparison between code base and base isolated. No, remember they have different performance. A code base building have the chance to collapse during an earthquake. Even the PBD, remember that even the building that were designed using PBD, there's still a 2.5 probability of failure. So meaning, if you have, for example, a 250 building, 25 of them or 2.5 buildings will still collapse. Okay. Now, if you compare that with isolated buildings, well, there's no more lateral force, less confinement, less reinforcement, less volume of concrete in the column and beam and shear wall. Don't you know that in our project, a 45-story building, when we use fixed base, we have a 1 meter thick shear wall, but when we use isolator, it becomes 0.5. So you can see that. Okay. So very minimal difference in terms of cost. Okay. Another question. For PBD, yes, I require a site-specific study. Actually, we conduct site-specific study. So my team, we have a team of earthquake engineers who conduct this site-specific study. Even the microthermal test, so we are doing that ourselves. Okay, so we have the tools, we have the equipment to do this. Okay. Another question. Hi, sir. What's the lifespan of the seismic isolator, especially during major earthquake? No, because if you use rubber, the strain of the rubber is 600%, zero damage. There's no debonding at 600%. So meaning if you have a 0.1 thick rubber, it can displace as much as 0.6 without damage at all to shear. Okay? So therefore, it will just go back to its original position without damage at all. Now, we cannot design that in real building. In real building, normally the strain is 100% to 200%. Meaning, if the thickness of the rubber is 0.1, it can deform only as much as around 0.2 maximum. Okay, so if the rubber has the ability to deform as much as 600% strain, well, that's too much. So practically, even to a very strong earthquake, the rubber cannot be damaged. Okay. Okay, any more questions? Any question? Uh, there are questions from the question and answer tab, and there are also questions from the chat, so I'll try to read both of them. Thank you, sir. Great lecture. Thank you, Engineer Malikad. Uh, is it possible to install isolation in non-isolation existing buildings? Yes, yes. As I've said, the LA City Hall is the tallest building with seismic isolation. So it was an existing building. That Los Angeles City Hall was constructed in 1927. It was hit by a lot of earthquakes already. And lastly, it was hit by the 1994 Northridge earthquake. But since they cannot demolish the Los Angeles City Hall, of course, that's the landmark. That's their landmark. That's a historical building. So what they did is they have to retrofit the building at all cost. So meaning we can really retrofit buildings with isolations. Right now we have I think around 20 buildings, existing buildings for retrofitting with isolators. Some of them are designed, some are them existing. Okay. Any other question? So I think we are also attended again from different parts of the world. Last batch one, we are attended from some of them were from US, some of them from all over Asia, I think. There are a lot of different countries where, who attended, no, or joined our webinar. Ah, thank you, Sir Ray Flordolesa, for joining again. I hope you're okay and you're safe. Everybody is safe, no, for to this pandemic. Okay, so by the way, RBRA plan to conduct one free lecture every month, and then of course 2 lectures every month. That is only 4 hours. So normally about introductions of, or we plan to have a, uh, topic about the detailing of reinforced concrete based on the ACI 2019. Okay, and what are the major changes? But you know, sometimes it's sad to read that book because they just say that we need to provide confinement, but all those columns and beams were allowed to be damaged during a very, very strong earthquake. So that's the sad part of that document. Okay, I hope that in the future we use the working stress design where we use elastic limit so that everything is elastic, then there's no damage at all during a very strong earthquake. Let's put some fuse in the building like electrical engineers. Huh? Electrical engineers, they put a fuse so that when there's a fluctuation of a high voltage, then the equipments and other what you call that, furnitures or equipments will not be damaged during that fluctuation of an earthquake. It's the fuse uh, that will give in before the for example, air conditioning or other electrical tools. Okay, and we also plan by next year, so we will have hands-on about the performance-based design of a 21-story. So this is an actual building. So this is also an existing building, our own project. I will share with you how we do the analysis using the performance-based design, and what are the acceptance criteria of the code in real building, in actual building. How do we analyze that? What are the procedures? But I think it will take us 2 days to have that, 8 hours and 8 hours. But maybe I will give you the model in advance for you to study, okay, before we will do the actual hands-on. And then, of course, what is important here is how do you interpret the result? That's very important. It's not just about using the software, but how do we understand the result, interpret the result, okay? Um, Otherwise, all the computer generated result will just be a waste if we cannot interpret that properly. Okay? Okay, so if there's no more questions, maybe I can wait for another minute. So if there are no more questions, then I will have to log out. Okay, again, thank you very much. Maraming salamat. Gracias. Ah, there's another question. Any books or reference for step-by-step procedure of PBD and RBD? Well, sometimes books is too much of a theoretical approach. So what you really need to read is the AC41, ATC, the NERP, Okay, so there's a lot of procedures about actual use of this design method, because if you're talking about books, or sometimes it's not really very usable. It's sometimes just for academic purposes that they have that exercises, but not it's not really for industry-based approach. Okay, so of course our modules, I have module 1 to 10, 1 to 12. Module 1 is about the introduction to or fundamentals of structural engineering. So that is a module where I teach that in 3 days. I teach you how to design a 5-story building using manual calculation. You just have to use calculator, ball pen, and of course paper. Know anything? Okay, so I'll teach you the shortcut method on how to design slab, beams, columns, including the footing. And then I have module 2 about concrete, module 3 about steel. In module 3, we discuss there in steel design. So we discuss about different types of design approaches, the notional load, what's a notional load when we design steel structure. Uh, and of course, we have module 4 about bridge. But in the design of bridge, I added some part of it to be a resilient design, because right now some of the code in ASHTO is already about PBD, but very few requirements about the resilient based design. But if you're going to go to other countries like even Thailand or even Malaysia, where there's no high seismicity, look at the bridges. They already install seismic devices. In Thailand, they use most of the time friction pendulum. But if you're going to Malaysia, they usually use a rubber or high damping rubber. Okay. Singapore is not a high seismic risk area according to them, but take note that that is very close to Indonesia, where Indonesia have a high seismicity. So maybe, uh, well, earthquake is not political boundary; it's a geologic boundary. So if you have to look at the map, Singapore is very close to the fault lines in Indonesia. So I don't know how it will affect, especially that Singapore is partly is clay. Okay. uh, about the books, maybe if you are teaching in the academe, the best book that you can use for the base isolation is the book of Kelly. That's one good book about the basic concept of isolation. But reading that book will not uh, teach you how to apply isolation in real practice. Okay. So another problem now about the design of isolation is sometimes the client will just say that, okay, can we just buy this type of isolator? No. Remember that we have to dictate, we as structural engineer must dictate the performance of our building. And the performance of our building is based on the properties of the isolator that you define. Okay, so what is the horizontal stiffness, the vertical stiffness, okay, the damping property of our isolators, so that we can achieve the performance of our structure. Okay, some of my clients say that, okay, why not just buy this isolator from somewhere else? No, it's not just like a doorknob that you can buy that doorknob and then just install that doorknob. So you have to design as a structural engineer the property of the isolator that you need in order to achieve a better performance of our structure. Okay. Another question, like PBD and RBD is applicable to all types of structure in horizontal and vertical? Yes. As I've said, bridges in other countries, they use already the resilient-based design. They use isolator. One of the biggest bridge construction in Japan, when we visited, they use already a lot of square isolators. Okay, and these isolators are made up of steel.
So we visited one of the bridges in Kanazawa. So that's in the west of Japan. uh, Sir, any recommended standard or guidelines for the performance-based design for non-building, especially electromechanical equipment? Well, you can use the non-structural component. No, that's the content of part of the content of the building. So you can use that, no, as part of the reference. Where does a plastic hinge develops in a structural member? Well, the plastic hinge is normally 2H from the face of the column if you use the design approach. And normally the plastic hinge should be the point where maximum moment occurs due to the generated lateral force due to earthquake. So in beam, normally that's the both ends. In column, the plastic hinge is the top and the bottom. Okay, so that's why in column we have that confined region. Confined region in the column is there are three values. Number one, 1/6 of the clear height of the column, or the bigger column dimension, or 450 millimeter. So that's it. But in beam is simple. The confined region is twice of the total height of the beam. Okay. When you cut existing column, it's not dangerous. Of course, it is dangerous. Construction is the most dangerous job in the world. One of the most dangerous. So when we cut the column to install the isolator, of course we have to monitor number one, the deformation, the drift. You have to use laser to make sure that the level will not change. You have to use the dial gauge. You have to use a lot of props, no, or shorings to make sure that it will not move. Okay, but in our project, we don't allow the occupants to evacuate during installation of the isolator. They can occupy the building while we are installing the isolator. Okay. Any more question? How much is the installation of the dumper? Well, the installation of the dumper is even cheaper than using conventional retrofitting. And then the installation of isolator is a bit higher than conventional. But the most economical type of retrofitting now is the dumper. You know why? Because if you use a damper, it is a damper that will dissipate the seismic energy, and therefore the reactions in the footing will not change. But if you're going to put a rigid brace, that brace will just stiffen the building and therefore absorb more earthquake energy, and therefore absorb a lot of lateral force that will cause pushing down the footing or pulling up the footing, in which you need to retrofit the existing footing. But if you're going to use a damper, whatever is the reaction due to gravity, that reaction is normally, or most of the time, higher than the reaction, even with earthquake, if you use the damper. So it's actually cheaper. Okay. So I'll just check. We still have enough time. I think there's no more question, relevant question. So just wait for uh, a day or two that we will email to you the slides, the PowerPoint. We will give you copy of the PowerPoint, and then also the electronic certificate. Now, if you want to apply to PRC for your CPD credits, then you can just go to directly to the PRC and bring that certificate for them to consider or put some or
evaluate and credit certain unit of points of certain points for your PRC renewal. Okay. Okay. So as I've said, our upcoming seminar this Friday will be the Tier 1. I hope you can join us. I, I would like to end this webinar again. Thank you very much for attending. Watch out for our webpage, RBRA Structural Engineering Hub. We teach what we do. We don't teach not just from a book, but we teach what we do. We share what we learn from our experience because we aim to have uh, a community that is resilient by sharing ideas of all the structural engineers, not only in the Philippines, but all over the world. God bless. Good afternoon and good evening to other part of the world. Thank you very much.